Hello and welcome to Hands-on DynamoDB for Developers by James Cross, and I'm the Head of Digital at Calibri Digital. So like I said, my name's James Cross. I'm a certified AWS Solutions Architect. I've got more than 10 years experience of designing and implementing Java applications, and really in the past 5 years I've been focusing on cloud native applications, particularly serverless, and I've got a speciality in serverless web services and big data applications, particularly on the AWS cloud. So rest assured you're in good hands. So let's jump in and have a look at what we're going to cover in this course. So what are we going to learn? Well, we're going to start with a good understanding of the data model of DynamoDB and compare NoSQL, document stores, and traditional relational applications. Next, we're going to work together to build a simple DynamoDB-powered application. We're then going to move on to build a more complicated application and use that as a way to understand query fundamentals, the query DSL, of DynamoDB and the difference between queries, scans, and indexes. Look at how we can scale out DynamoDB to build hyperscale web applications. Next, we're going to build a data cache with DynamoDB and leverage DynamoDB's TTL feature. Then we're going to look at how we can get data out of DynamoDB in real time using streams. And lastly, how we can create ACID transactions on DynamoDB. So plenty for us to focus on. Now, some basic programming knowledge is assumed. I'm not going to teach you how to code in this course, but if you've programmed in any high-level programming language, you won't have any trouble following along. In terms of prerequisites, well, really, like I said, some level of prior experience in a high-level programming language, and of course, you're going to need a computer. And if you want to follow the code examples and actually build stuff yourself, you're going to need an AWS free tier account and obviously a connection to the internet, and you'll also want to install the AWS CLI on your computer, and you're going to want to install Visual Studio Code or some other equivalent text editor. So what are our goals for the course? Well, hopefully by the time you've watched this course, you'll come away with a good understanding of NoSQL and how it differs to a traditional data model. Hopefully you'll understand how DynamoDB helps us to build cloud scale, hyperscale applications for the web. We're going to put the fundamentals of DynamoDB into practice. We're going to learn how we can use things like secondary indexes for greater query flexibility. We're going to understand how we can accelerate the performance of DynamoDB further with DAX. We're going to build a data cache using TTL, and hopefully you'll understand as well how to export data with streams and create ACID transactions. Everything you need to get started with DynamoDB. Enough of the introductions, let's jump right into the content. Welcome back and welcome to section 1, the DynamoDB data model. Welcome to video relational databases versus NoSQL. So there's going to be a lot of data buzzwords in this course, and I thought it would be helpful just to set these out right up front so we're all on the same page. So firstly, we've got the relational database. So a relational database or relational application database is where data is organized into tables against which queries are run. Now, anybody who's following this course who's got any kind of development or technical experience has probably worked with a relational database at some point in time. Perhaps you're thinking about, sometimes these are referred to as SQL databases, and typical examples are MySQL, SQL Server, DB2, Oracle database, those kinds of things. And typically, the way this works is data is laid out in tables. You write SQL queries to retrieve data from those tables, and the database engine executes those SQL statements for you. Another buzzword is the data warehouse, and the data warehouse is basically a centralized relational data store for business intelligence. So the data warehouse came about as relational databases were adopted more and more by businesses. Businesses realized that their data was becoming siloed in lots of different application databases, and that meant there was no way for a business to create business intelligence across all of these different databases. So the data warehouse is a way of pulling data in from all of these relational data silos into a centralized data store to enable business intelligence. Now, NoSQL is a really, really broad term. It's a typical example of the IT industry getting excited about something new, and it's a really broad term categorizing any database that can store data but cannot be queried with SQL. So NoSQL is exactly as the word implies, is everything that's not relational. So very, very broad sweeping term. As this is a DynamoDB course, DynamoDB is an example of a NoSQL database. And lastly, big data, and I've put that in quotes for a very good reason. So officially this means absolutely nothing at all, but everybody seems to be talking about big data. Everyone says they've got big data, But really what we mean is when we talk about big data, we're usually referring to the tools that you use to process data in a way that can be scaled out horizontally. So in terms of the relational database fundamentals, probably you're familiar with this, so I'm going to keep it very brief. In a relational database, data is organized into one or more tables. Each table is made up of rows, and a data point in a database is a row in a table. And a row represents a single item, and it must be unique within the table. A column in that table represents a named attribute of that row, and all rows within the table must adhere to the table's defined schema. And the important thing about relational databases, one of the big differences we'll see between relational databases and NoSQL databases is that all rows must adhere to that table's defined schema, and that schema is defined up front when the table is created. So here's a very, very simple example of a relational database table containing information about training courses. Down the left-hand side, the first column, we have course ID. In a relational database, each record usually has a unique identifier. So in this instance, that's course ID. Then we've got course name, location, and cost. So we can see that each entry in that table corresponds to a training course. That's a row. There are a lot of very, very popular relational database engines, the most popular or the most well-known being Oracle, SQL Server, MySQL, Postgres. Amazon Aurora is quite a new one, and MariaDB as well, which is an open source optimization on top of MySQL. So enough about relational databases. What is DynamoDB? And this has been taken from the Amazon product page. So Amazon tells us that DynamoDB is a fast, scalable, and fully managed NoSQL database service. DynamoDB supports both key value and document store models. And the proposed use cases for DynamoDB are web, mobile, gaming, IoT, and other apps that need consistent latency. So very, very broad sweeping statement there. Again, DynamoDB is a fully managed Amazon provided service, so it's database as a service. And as we'll see in a few slides time or in a few videos time, what that means is Amazon allows you to consume DynamoDB just based on an API. So we don't have to worry about standing up infrastructure. We don't have to worry about managing servers or updates or anything like that. Amazon does all of that for us. We just tell it what we want to create. Amazon creates the infrastructure for us, and we just consume DynamoDB from an API. So let's try and make sense of all of this. If we were to put all of the data technologies we've just talked about onto a graph, what would they look like? Well, if we plot them, scalability versus query response time is probably the most sensible way to do this. We can see that NoSQL databases are both the most scalable and offer the fastest query response time. Relational databases, so RDBMS, Relational Database Management System, they offer an equivalently good query response time as NoSQL databases, but they're harder to scale. Data warehouses are easier to scale than a relational database system, but their query response time tends to be lower. Big data systems are perhaps even more scalable than NoSQL databases, but they also take the longest to provide an answer to your query. So based on this, NoSQL is the winner. Or is it? Well, let's just perhaps slow down a second. So NoSQL databases can be very loosely classified by the data structure that they support. And you've already heard me mention the terms key value and document. So what do these mean? Well, a key value store is basically like a persistent map. So if you've ever written an application in Java or Python or in fact any programming language, you've probably used a map data structure at some point or another. And with a map data structure or a dictionary, depending on the language that you're programming in, you can retrieve data based on the key, but it's very difficult to retrieve data based on the value. So it's a mapping of a unique key to some value. Key value NoSQL database is like a persistent map. So only the key is indexed, and fetching by value is very, very expensive. So Redis is a common example of a key value store. A document database is like a key value store, but with the ability to index some elements of the value as well. So that means if you don't know the key, you can create an index on some of the values and do a lookup on those values. And MongoDB is the most common example of this. Columnar databases are quite different. So in columnar databases, it's like a relational database, but everything is pivoted by 90 degrees. So data is stored by column instead of by row, making it better for scanning subsets of the table. And Cassandra is an example of this. And the last data model, or the last common NoSQL data model, is the graph database. In a graph database, data is stored as a collection of nodes and edges, making it possible to query the relationship between them. And the most common example of this is Neo4j. Now, the thing about data structures is that they limit query flexibility. So NoSQL databases scale really well and respond very quickly because their data structures are optimized such that they can be easily partitioned across multiple servers, and that's why they scale so well. The downside to this is that the query DSL is significantly more limited compared to a relational database. And you actually need to model your data with your application's access pattern in mind from the start, otherwise you kind of tie your feet together. And getting this wrong can be very messy, and we're going to see an example of that a little bit later. So if we had to compare these tools again, and this time trading query flexibility for query response time, actually NoSQL is not the winner anymore, because although it offers, the best query response time, or, at least equal to relational database models, the flexibility of your queries, or the query flexibility, is very limited. And in this regard, a relational database, is the winner. So really, when we're comparing database technologies, we need to look at our requirements for query flexibility versus scalability. And as we can see, a data warehouse is perhaps slightly less flexible than a relational database system, but also slower, and a big data model is, less flexible again and also slower. So that's everything I wanted to talk about in this video. Please feel free to move on to the next video where we're going to talk about the DynamoDB data model. Welcome back and welcome to video the DynamoDB data model. So, fundamentals of DynamoDB. Data is organized into tables, and tables, just like in a relational data model, are collections of data. Inside tables you have items, and items are individual entries in your table, similar to rows. And lastly you have attributes, and attributes are the properties associated with the entries, kind of like columns in a relational data model. So actually, data is stored just like JSON, and really that's the best way to think about it. So let's say we had a DynamoDB table containing information about movies. We would have perhaps some attributes: title, year, rating and genres, and they'd be structured like this. So title, this is This Old Tale, year 1920, rating 7.2, and an array of genres. Now, one of the cool things about DynamoDB is that not every single element in the table, or not every single item, to be correct, syntactically correct, not every single item has to have the same attributes. Some can have more or less than others. So for example, This Old Tale may just have title, year, rating and genres, whereas The Great Sailing Trip of 2015 might have extra info as well about actors and awards and other things like that. So that allows you to have much greater flexibility than a relational database when it comes to storing your data, because your schema can evolve with time. Not all objects and items necessarily have the same fields. Some items might have more, some might have less. DynamoDB doesn't care. As long as all items have the primary key that you've defined when you create the table, everything else is completely optional. So under the hood, DynamoDB uses solid state drives to store the data, so it's very fast. DynamoDB automatically and synchronously replicates data across 3 facilities in a given region, so 3 availability zones. As we've just discussed, the schema is very flexible. There's no limit on the amount of data stored in a DynamoDB table. However, the maximum item size is 400 kilobytes, so do bear that in mind when you're designing your tables. And DynamoDB also supports cross-region replication, a feature called global tables. So, fundamentals continued. There are 2 types of consistency. Eventually consistent reads, which is the default option. That maximizes the read throughput available on a table. It takes approximately 1 second for data to be replicated to all facilities. If you write an object and then you go to query again, within a second you might get a stale version of your data, so you might need to repeat the read. And the second option is something called a strongly consistent read. And what this does is that the result reflects all the writes that got a successful response before the read. So that means basically your read operation is directed to the same node in the cluster as your write operation. DynamoDB scales through provision throughput capacity. You've got 2 options, or two types of throughput capacity: read throughput and write throughput. And it's very flexible. You can just increase and decrease the read and write capacity as you need using the update table API. And Dynamo achieves this with no downtime whatsoever, so you can continue to read and write to your database as you perform this operation. DynamoDB requires a primary key. So you can have a single attribute primary key called the partition key, otherwise known as a hash attribute, because it's a hash operation on the data you put into that field that determines the primary key. And that is unique within the table, so that's for a single attribute primary key. Or you can have a multi-attribute primary key, sometimes known as a composite key. And this is made up of a partition key and a sort key, sometimes known as a hash and a range key. And this allows you to have items with the same partition key, but with different sort keys. And DynamoDB enforces that sort key must differ. So if you try and write a duplicate object with the same sort key, you're going to get an exception. DynamoDB also supports something called secondary indexes. This is to allow you to have greater flexibility when it comes to querying your table. And there are two types of secondary index. So one is called a local secondary index. This is secondary indexes that have the same partition key as the table, but a different sort key. And these can only be created when you create your table. And you can have a maximum of 5 local secondary indexes per table. And next there's something called a global secondary index. So this can have a partition or a partition and sort key that can be different from the tables. They can be created both when you create the table or at any time in the future. And again, you can have a maximum of 5 global secondary indexes per table. So that's everything I wanted to talk to you about in this video. Please feel free to move on to the next video where we're going to look at a simple DynamoDB data model example. Welcome back and welcome to video simple DynamoDB data model example. So what are our requirements? Well, we want to create a database that can hold information about users that access our system. And we're going to need to store things like first name and last name, email address, password, and the last login time, along with a user ID for lookup and some user preference information. And the intention is that we'll only ever look up users based on their email address. So when it comes to designing the table, DynamoDB is designed in such a way that we need to provide a small number of parameters up front, the smallest number possible really. So based on our requirements, if we want to be able to query based on email address, and only ever on email address, we're going to set our partition key or primary key as email address, and we're going to set a sort key of last login. So we're going to store this as an epoch time in milliseconds. So what would that document look like? Well, it's really simple. So email address is our primary key. So email address perhaps is joe.blogs@gmail.com. The last login is, and this is an epoch time. The password, we're going to store just a hashed password. My first name obviously is James, last name is Cross, and then my user preferences. So, and again, the nice thing about DynamoDB is that this is completely flexible. So another user, Joe Blogs, might have different attributes here. But let's just say, for me, my favorite color is blue. My favorite football team is Manchester United, and the current products I have from this company are a credit card and a current account. So very simple. So that's absolutely everything I wanted to talk about in this video, a very quick one. We do keep in mind the example that I just gave you because we're going to use that in future practical examples. Feel free to move on to the next video where we're going to look at how we can create our very first DynamoDB on the AWS console. Welcome back and welcome to video creating your first DynamoDB table with the AWS console. So prerequisites to be able to follow along. You're going to need a working AWS account that you can log into with administrative permissions. Ideally, administrative permissions are not required, but you're going to need access, obviously, or the ability to create DynamoDB tables. And later on, you're going to need to have access to be able to do that programmatically, to create Lambda functions, to create API gateway endpoints, and to create and delete CloudFormation stacks. That's kind of the minimum. IAM is also going to be important, the ability to create IAM roles. You'll also want a text editor and a terminal. That's going to help if you want to follow along with the programmatic examples. And having Python, pip, and also the AWS CLI installed and working is going to help a lot. So let's go. Let's go and create our first DynamoDB table. So I've just flipped over to the AWS console here. You can see that I'm logged into my Calibri Digital account. And this is the home page for the AWS Management Console. So what we want to do, obviously, is head over to DynamoDB. You can see I've pinned it up here, and it's also in my recently visited services. You probably won't have that. There's two ways you can find it. You can click on Services, and you will find it under Database. You can also start typing DynamoDB, and that will pop up with a filter. Or you can just start typing in this box here, DynamoDB Manage NoSQL Database. So let's click on that. and Amazon's going to give you the Amazon DynamoDB product page. And you can see I've got some of my information for the slides from here. Amazon DynamoDB is a fast and flexible NoSQL database service for all applications that need consistent single-digit millisecond latency at any scale. Its flexible data model and reliable performance make it a great fit for mobile web gaming, ad tech, IoT, and many other applications. Should all be very familiar by now. But actually, Amazon make it really easy for us to go and create our first table. So let's click Create Table. And you can see here, Amazon's not really asking for an awful lot of information. So table name, we can have my first table. We can set the partition key, let's say to email address. Let's add a sort key of last login. We're going to change that from string to number. And then we can configure some other options for our DynamoDB table. Amazon suggests some defaults. We can untick that. We can add secondary indexes. We can add provision read throughput, or a new feature called on-demand throughput, so Amazon scales the table for us. Obviously we can modify our provision capacity here if we want to. If we select on-demand, we don't have the ability to do that. We can auto scale our table if we wish, and we can also specify encryption at rest of our data if we want, but we're just going to go with the default settings for now, and then we click Create. And I'm just going to pause the video while the table is created. It'll only take a few seconds. So that's it. My table's created. It took less than 10 seconds. And this is our first DynamoDB table, and we're now ready to start interacting with it. And you can see we've got a lot of options across the top here for things that we can do with our table. But perhaps the most important is items. So we don't have any information or any data in our table right now. So there's nothing really for us to interact with. But this is quite a nice way for you to view the data that's in your DynamoDB table. You can scan and query your data. Obviously, you can add filters and that kind of thing. If you're running a query, you can only query on partition key and sort key. And you can sort ascending or descending. You can pick projected attributes if you're on a secondary index. You can configure TTL, which is something we're going to do a bit later. You've got lots of options, and I encourage you to just click around and have a play if you're interested. But what we're going to do for now is just delete that table. We don't need to create a backup because there's nothing in there. Let's just delete it. And in the next section, we're going to start creating things programmatically. So that's everything I wanted to show you in this video, and in fact everything I wanted to show you in this section. Please feel free to move on to the next section where we're going to start to work on DynamoDB tables and create some DynamoDB examples programmatically. Welcome back, and welcome to section 2, building a simple application powered by DynamoDB. Welcome to video 1, modeling a user management application with DynamoDB. So, what are we going to build? Well, we're going to build a system to store users' favorite training courses. I'm sure all of my training courses are your favorites, but what we want to do is just take this example and build an API, some Lambda functions, and a backend DynamoDB to store different users' favorite training courses. So we want to create a database that can hold that information, particularly about users and their favorite training courses. And we need to store things like first name and last name, of course, email address, password for them to log in, the last login time as an epoch, a user ID, and some user preference information. A user table will store information about users and the IDs of the courses that they like. And we're going to need a second table to hold detailed information about training courses that users like. Now remember, DynamoDB doesn't support joins. So that means if we're ever going to need to run a query that retrieves data from both tables, our application is going to need to handle the logic to perform that join operation itself. So a typical microservices architecture, the table that holds information about training courses would live in another service entirely. So our application or front-end client will be responsible for calling both of those services and presenting the information itself. So we need to be mindful of this fact when we design our tables and our application. So, data model. We've already looked at this data model in the previous section. The partition key is going to be email address. Our sort key is going to be last login. We did this when we created a DynamoDB table from the console as well. And then our favorite courses will just be stored in an array of course IDs. And we're also going to have a course information table. Again, data model is very, very simple. The partition key or primary key is going to be course ID, so we can retrieve information about training courses by course ID. And then obviously we're going to have title, we're going to have published date, we're going to have author name, and we're going to have subject area. Now, I want to call this out again. DynamoDB is a NoSQL database, and that means that the query model is quite limited, quite simple. We can't do joins across tables, we can't do aggregations, we can't do, min, max, group by, that kind of thing. All we can do is query by primary key and sort key. We can scan the table, which means basically looping over every record to find what we want, and we can apply filters and sorts, and that's really just about it. And we're going to cover this in a lot more detail in the next video. But with this data model, we're saying that in almost all use cases, and I mean more than 99% of use cases, we'll only access users based on their email address, and we'll only ever access courses based on their course ID. Now, if we just go back a moment, if we decide we want to access users based on user ID, with this table model, we can't do it. If we want to find all users that are called Joe, we can't do it. DynamoDB doesn't let us do that unless we do a scan, and as we'll find out in the next video, scans are really, really bad. Now, there are a few workarounds using secondary indexes and that kind of thing, and we'll talk about the positives and negatives of that approach as well. But for now, let's just assume that we can only access users based on email address, and we can only access courses by course ID. We won't be able to search by author name or published date or anything like that. And it's really, really important. If we want to search based on other parameters, things are going to get complicated. So that's all for this video. Please feel free to move on to the next video, and we're going to look at the importance of understanding query patterns. Welcome back, and welcome to video 2, the importance of understanding query patterns. So before we begin, and I'm going to keep re-emphasizing this because it's a really, really important thing that we understand. The DynamoDB data model is like a persistent map. We need to think about it as a hash map or a dictionary. Okay? You'd never write your Python or Java application in such a way that it relies on scanning the values in an in-memory map, because apart from just being really, really stupid and really poor programming practice, it's really, really slow. Okay? The reason you use a map or a dictionary is because you know the key that you're going to look up on. Right, that key will be some ID, some unique ID. Key can obviously only ever exist once in a map or a dictionary, and we know what that key is. We're only going to look up objects based on that key. You always access a map based on its keys, because a key lookup returns in O1 time, so it's constant time complexity. It doesn't matter if you've got 100 or 1,000 or 100 million or 100 billion objects in your map. Assuming you've got enough memory space to store that amount of data. Doesn't matter how much you've got in there, a lookup on the key will return in constant time complexity. Order 1, that's what we say. It's big O notation, big O1. Okay, it's a really, really important point, because as the table grows, or as your map grows, it continues to take the same amount of time to retrieve something from that map. If we didn't know the key, we would have to search through all values in that map. Now, on average, that's going to take O(n) over 2. Well, it means that if your table doubles in size, the amount of time taken to locate the object you're looking for will also double. So that means, it might perform well while you've got 100 objects or 1,000 or 10,000. But if you've got 1,000,000 in there, it's going to take, 1,000,000 times longer than if you had one object. So that means that searching the values will get slower as the data structure grows in size, whereas a lookup on the key will not. And that's a bad thing. If it gets slower as you get more data, you've done something wrong in your system design. So DynamoDB offers two fundamental ways of getting data out of the database. First of all, it's a query, and that's a lookup on the key or the primary key. So it allows us to retrieve one or more items using the table's primary key or from a secondary index using the index key. For a query, you need to specify a partition key and a search value, or optionally a partition key and a sort key. So if you've got a composite key, you specify both parts of that key. And DynamoDB will return all attributes of the matched values, or you can use a projection expression for a subset of those values. You can also filter the query results using filters on non-key attributes, something called a filter expression. But a filter gets applied after the results have come back. It's just that DynamoDB executes it server side for you. DynamoDB supports both strong and eventual consistency, although eventually consistent is the default. Remember, that means that if you do a write operation and then perform a read operation very soon afterwards, you might get stale data. And that's because DynamoDB is a cluster under the hood. So it's a cluster that spans 3 different data centers, and obviously it takes some time for your changes to get replicated across those nodes in the different data centers. And DynamoDB, that means the results are eventually consistent. So it will take some time for the changes to be replicated, and therefore it will take some time for those changes to be visible. The maximum size that can be returned in a single query is 1 megabyte. Query results are by default sorted in ascending order by sort key. To get results in a descending order by sort key, you use something called a scan index forward equals false flag. Now remember that a query is the same as doing a lookup on a key in a map. It's O1, it's constant time complexity. If your table grows to 1,000 terabytes, it's still going to take less than 10 milliseconds for DynamoDB to return the result, which is really quite something, really very important feature of DynamoDB, but also a very impressive piece of engineering on Amazon's part. Scans are the exact opposite. So scans get all items and attributes by performing a full scan across the entire table or across an entire secondary index. So DynamoDB will retrieve everything, and then it will filter out values to return the wanted result, which is a second step. Now you can obviously limit this result set by specifying filters against one or more attributes with a filter expression, against the attributes to include, which is called a projection expression. But the bigger the table, the slower the scan. This is the equivalent, the literal equivalent of writing a for loop. You're saying loop over every attribute in my list until I find what I'm looking for. So that means as the table grows, it's going to take longer and longer to get your results back. As with a query, the max return size is 1 megabyte. By default, the reads are eventually consistent, and you can set consistent read to true if you want. Scans are by default sequential, so like I said, it's literally a for loop. And if you start doing a scan on a large table, you're going to massively, increase the consumption of your provisioned indexes. So that means if you've provisioned a certain amount of throughput on your table, if you perform a scan on it, you're going to see that you consume that very, very quickly. There are a few options to get around this. You can do something to reduce the page size, so limit the number of items that get scanned at once, or you can isolate scan operations away from your production table. But either way, what I want you to understand is that a scan is a compromise. If you're having to scan your table, it means you probably designed something wrong. There is the possibility of doing parallel scans, and with this the total segments is equal to the number of workers that perform those parallel scans. But it can consume all of your read throughput and throttle your table, and scans are massively less efficient than a query operation. So again, if you find yourself regularly needing to scan the table, you've done something wrong. But what happens if we need to query another field that's not our partition key or our sort key? Well, what we can do is we can define either a local or a secondary index, and we'll go into this in detail a little bit later. We can have a maximum of 5 of each of these indexes. And what they do is they essentially create a copy of the table in a second DynamoDB cluster, which is then kept in sync with your primary. So this allows you to define a secondary partition key or sort key on your table, which you can then query. But beware, there is replication latency, and by their very nature, secondary indexes are eventually consistent. So that's it for this video. Please feel free to move on to the next video, where we're going to create a simple Python API to manage users and their favorite training courses. Welcome back and welcome to video 3, a simple Python API to manage users and their favorite training courses. So what are our requirements? Well, we want to be able to create and get a single user. We want to be able to add new favorite training courses for a given user. And we want to be able to create and get a single training course. So very, very simple. And of course this leads to a natural REST API design. When we want to create a new user, we want to do a put. So put /API root /users/user ID. We want to be able to get, again, we'll do /users/username or user ID. Put /username/course ID to add a new favorite course. A put to /API/course is to create a new course. and a get to /API/courses/course ID to get a given course ID. Now, in terms of technology choices, we're using DynamoDB, so it makes sense that we want to use other AWS native technologies. So in that scheme, we're going to use API Gateway, we're going to use Lambda, and of course, we'll use DynamoDB for storing data. We're going to write all of our Lambda functions in Python, and we're also going to create an AWS SAM template to automate the creation and deployment and update of the stack. So with that said, let's go and take a look at the code. So I've created everything here that you need to get started, and I've opened the project in VS Code. And what you will see down the left-hand side here is there are multiple sections where each section refers to code examples for the course. And if you expand each section, you'll see that there's various part numbers where one is for each of the videos in the course. So we're currently on section 2, video 3. So the thing you want to be looking at is section 2, part 3. And you're going to see a bunch of files in here. So these Python files are the source code files for each of our Lambda functions. So if you don't know what Lambda is a code execution as a service technology provided by Amazon. It allows us to upload some code and Amazon run it when an event that we define happens. So in our case, that event is going to be an API call. So the technology stack is very, very simple. It's going to be a REST API call to an API Gateway endpoint. API Gateway invokes a Lambda function, which is the code in these Python files here. And that Python file, or that Python Lambda actually, will be granted permissions to do something to one of our DynamoDB tables. Amazon makes it all very easy to create this microservices structure for us with a technology called SAM, or the Serverless Application Model. So SAM is a templating language that allows us to define a service, a web service, based on predominantly on these three technologies that we've talked about, API Gateway, Lambda and DynamoDB, and bind them all together. So this is really just a manifest file that explains what our environment looks like. And it's really, really cool because it allows us to then run something on the command line. You can see down here I've been doing some stuff to test my work. It allows us to run a command on the command line and stand up the entire AWS stack and then run another command to shut it down. And this process is called infrastructure as code. So the file I've got open here is called template.yaml, and that is that SAM template, and that defines all of the things that we're going to create. So I'm just going to walk you through that very briefly now. So at the top here is just some templating. We're saying that the execution timeout for our functions will be 30 seconds. And we've also set some environment variables here that we're not going to use at the moment. But what happens is these environment variables get injected into all Lambda functions that are defined in here. So that's under globals. Next we have the resources section. Notice this is YAML. Under the resources section we define functions and our DynamoDB tables. So in this particular example we don't have any DynamoDB tables, but in the next video we will. So what we've got here is our functions. So these correspond one-to-one to these 5 functions here. So we've got a create user function, and what we're saying is an AWS serverless function, and these are the properties for it. So all of the code lives in the same directory as the SAM template. The handler method for this function is create user.lambda handler. So we can go and look at that code here. So create user.py, and we can see there's one function, lambda handler, and this contains the code that gets executed when our API is called. Now we're saying we're running under Python 3.7, and the events that will trigger our function create user event, and that create user event is a type API call, and the properties for that API call are that it's going to have the path /users/user ID. So if we go back to our PowerPoint here, we can see the same thing. So our API /users, and there's going to be a user ID path parameter there, and the HTTP method is put. And we've done exactly the same thing for get user with a get method, add course with a put method, create course with a put method. The difference obviously being add course is to add a favorite course for a user, create course is to create a course in the course table, and the get course function, which obviously is a HTTP get as well. So if we go and look at the code for each of these, at the moment it's just templated out, so we're not actually making any calls to DynamoDB. We're going to be doing that in the next video. So create user just takes the request body from the API body payload and gets the user ID path parameter and just returns a message saying you've asked me to create a new user with this request and this user ID. And if you go and look at each of the functions, you can see that we've created these in exactly the same way. The only other thing that you might want to know There's a README here with some useful commands that you might want to run against your infrastructure. And we've got a requirements.txt file which sets out the dependencies of our application. So what we want to do is we want to actually go and create our infrastructure now. We want to create our API gateway and our Lambda functions. So I've put the command you need to do that in the README. So just make sure you're in the same directory as this template file. So if you open terminal in VS Code, it should do that for you. But you can see here I'm in section 2, part 3. And now what I'm going to do is run this SAM package command. Now note that it references an S3 bucket, so make sure you've created an S3 bucket in your AWS account and swap that out. In all future SAM commands, you need to make sure you reference that S3 bucket, and that's where the command line is going to upload your code to, your code package. So we're going to run package, which will perform that upload operation. And you can see here successfully packaged artifacts and wrote output template to the package file. Now we're going to run a deploy command. So SAM deploy, reference that new package template, stack name I've called PyCharm demo, and this just says that it's going to have the required IAM permissions to perform that role. And then we're going to execute that, and this might take anything up to 2 or 3 minutes. But what we can do, we can go and have a look on the console as well to check what's happening. So on the AWS console over here, I've opened the CloudFormation service, and you can see that this stack is being created, create in progress. So if I click on that and click on events, you can see that it's actually creating all of this infrastructure for us. It's creating roles for each of our functions, and it's creating functions. Once this has been completed, it will start creating the Lambda functions for us, and we can see that happening there. So I'm just going to pause the video while that executes, and then we'll give our API a little test. So that's just finished. I can see successfully created or updated stack PyCharm demo. And if I go over to the AWS console and go back to stacks, I can see that that's now in the create complete stage. So the next thing I'm going to do is get the invoke URL for my API gateway. So if you click on services and type API gateway, just open that in a new tab. And you can see here we've got a new API PyCharm demo. I'm going to click on that. I'm going to click on stages, and I'm going to click on prod. And you can see here this has given me an invoke URL. So I'm going to copy that, and I'm going to open up Postman. So Postman is a really handy tool for testing APIs. So let's say I want to test the create user function. We're going to do a put. I'm just going to update my invoke URL here. So it's the invoke URL we've copied, /users /a user ID, and this can be ABC1234, it doesn't matter. And the payload that we need to create a user, so obviously email address, first name, last name, and password. I'm going to click send, and you can see you've asked me to create a new user with email address, first name, blah, 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 and user ID ABC1234. Now, if we just go back to our Python code for create user, we can see this is what's been executed. So that's everything I wanted to talk to you about in this video. We haven't yet started persisting data to DynamoDB, but what we have done is got a good example of how we can create a stack using a SAM template and a little bit of an overview of what our architecture is going to be for future videos. So please feel free to move on to the next video. We're going to modify our code to start storing user data in DynamoDB. Welcome back and welcome to video 4, storing user data in DynamoDB. So in the previous example, there was no database integration. And in this example, we're going to expand our code solution to persist users and course information to DynamoDB. This will obviously involve adding IAM permissions to our Lambda functions, as well as creating a DynamoDB table using our SAM template. So let's go and take a look at the code. So I've still got this open from the previous video. I'm just going to clear my terminal output at the bottom there and close everything I've got open. And what I want you to do now is open part 4 and go and take a look at the SAM template. And there's a couple of things that you're going to notice that have changed. So first of all, we're now creating DynamoDB tables in our resources section. So the way this works, it's quite straightforward. You say, I'm going to want a users table and a course table. I'm going to call one of these users table, and I'm going to call one of these course table. So what I need to do is define the attributes I want in my schema. So I want a user ID and I want last logon, and I'm setting the user ID as the hash key and the last login as the range key. So that's the same as partition key and sort key, and I've got 2 read and 2 write capacity units on my table. Likewise for the course table, The only attribute we're interested in is course ID, and that is going to be the partition or primary key. Just to note, the S means that the type of the attribute is a string, and the N means it's a number. The only other changes to note are that we've given our Lambda functions permission to read and write these tables. So Amazon has a managed policy called DynamoDB CRUD policy, so that means create, read, update, delete, and all you have to do is say which table that function has permissions to perform those CRUD actions on. So of course the create user function only needs access to the users table, get user function needs access to the users table, the add course function needs access to both tables because it's going to essentially update the course table as well as update a user object. Create course handler only needs access to the course table, and so on. Now, the really interesting thing here is that we've modified our Python code to access DynamoDB as well. So let's start with add course. So you see the code has become a little bit more complicated now. So what we're doing is we're using Boto 3, which is Amazon's Python AWS library, to interact with DynamoDB. We're getting the name of the table from an environment variable, and we're getting the DynamoDB table here. As before, we're using our Lambda handler, so we're getting the user ID from the path parameters, as well as the course ID that we want to add. So this is to add a user's favorite course. And then we're finding user ID based on their last logon, and then we're going to add that course for the user. So to get a user, we do a query, so it's a lookup on user ID here, and then we want to get the first result for that user ID. And then when we add a course, it's a little bit more complicated because we're going to use something called an update expression. So because we're actually appending a course ID to an array here, if you recall, the structure of our DynamoDB object was that it was going to have a list of a user's favorite courses. So what we want to do is append a new course to that list. So we use something called an update expression. So we're saying for this user and this user's last logon, because remember our key is composite, it's user ID and last logon. So this specifies the item that we're going to update. This specifies the expression that we're going to run against that item, and then the values and names for that expression. So we're saying set attribute name, which is favorite courses. So set favorite courses, and the action we perform on that is a list append. We're going to append to the favorite courses list a course ID. So we're adding a new course ID to that list. And that's all that function does. Likewise, create course, we're going to take the JSON payload from our API request, and we're going to create a new course with that contents. So in order to create a course, all we have to do is perform the put item operation. So we create a request object, course ID, title, published date, author name, subject area, and then we just run a put item on it. And if there's any exception, the Lambda function is going to fail and print out a helpful error message. For create user, we've done exactly the same thing. We create a request object, and then we do a put item on it. And we've also created a little very simple function here to encrypt a user's password. So that's just doing a SHA-256 on a user's password. For get course, obviously we're going to want to do a query. So we've created, again, the function is almost exactly the same. We've added this get course by ID function. We're going to do a query on the course ID. So we create this query request, a key condition expression where the key is the course ID. So we're going to do a lookup on that. So you do table.query, provide the key condition. That's, again, just a lookup on the key, and we want to get the first course that matches that ID. And get user works in exactly the same way. Get user by ID is a key condition expression on the user ID. So what we're going to do, we're going to package that up, and we're going to deploy it, and then we can go and have a look at the DynamoDB tables that have been created. We can make a few API requests, and we can make sure that the data is being updated. So what you'll need to do if you're still in part 3 is go into the part 4 directory, run the package command, followed by the deploy command, and I'm just going to pause the video while that runs. So that's just finished running. So the first thing we want to do is head over to the AWS console. We can see update complete, and let's go and have a look at DynamoDB and make sure that our tables were created. Click on tables, and we can see now we have 2 shiny new tables. So that's really cool. We've created that using a SAM template rather than from the console, so it's nice and easy to repeat. Now, of course, what we really want to do is actually put something in those tables. So first of all, let's go and create a user. So we can drop this, and what it should do is generate a UUID for a new user for us. So let's click send, And we can see we've got a response back pretty quickly. You've asked me to create a new user with this user ID. So we're just going to copy that. Let's go and have a look at the DynamoDB console. Click on Users Table, click on Items, and as if by magic, we can see we have a new user ID. And we can click on that, and we can now see the contents of that user object is exactly what we had in our PowerPoint slide. So that's very good. Everything seems to be working. Now, if we wanted to get our user from an API method, we would just go down to Get User, put that user ID on the end there. And of course, we also need to make sure that invoke URL is the same. Every time you delete the stack and create a new one, that invoke URL will change. So if you see things stop working, it may be because your invoke URL has changed. Remember, you get that from the API Gateway console. Click on Send. And with a bit of luck, oh, seems like we've got something wrong there. And that's because I have got the wrong user ID on my clipboard. So if I just, I'm on Get Course, would be why. So that's the user ID, and this is the invoke URL. Save that and click Send. And there we go. We can see that the user has come back just as we expect, but without the courses and without the password. Of course, we don't want the password there. So let's now go and try and create a course. So again, let's just make sure that our invoke URL is up to date. Don't need that. And let's click Send. You've asked me to create a course with hands on DynamoDB, da-da-da-da-da. The details were saved just like this. So now if we go and look at the DynamoDB courses table, we can see we have a shiny new course. Now to prove that that works, if we try and get a course or reload a course using our get method, obviously put the right course ID in the URL parameter, we can see that that comes back as we expect. Now the last piece of the puzzle, add course to user. So what we want to do is update a user object with our favorite course. First thing to do is put the right invoke URL in there. So let's just copy that over, add user to course. The next piece of the puzzle is the user ID, which is this piece here. So let's just copy that from DynamoDB. There's our user ID. Oops. And our course ID. So we're saying this new user has this course in their favorite course list. So let's put this here and then click on Send. User information updated. So now with a bit of luck, if we go and look at DynamoDB, that course ID should be in our favorite course list. So we click on Users, click on User ID, and we can see in the favorite course list we've got one object. If we expand that, we now have the ID of our favorite course. So that's everything I wanted to show you in this video, and in fact everything I wanted to show you in this section. Please feel free to move on to the next section where we're going to look at some more advanced DynamoDB features. Welcome back and welcome to section 3, Data Retrieval Fundamentals, Queries, Scans and Indexes. Welcome to video 1, Retrieving Data by Key, Queries. The data model is everything. Now remember back in section 1 we talked about how NoSQL databases trade query flexibility against performance, scalability and high availability. Understanding these limitations combined with your application's use case is absolutely critical to designing an effective data schema. Failure to do so can result in really high usage costs and poor performance. Now, I've been working as an AWS architect for some time, and this is the #1 mistake that people make when using DynamoDB. Because Amazon talk about it like it's a general purpose database, developers in particular think it can be used in the same way as a SQL database, something that they're used to. And in fact, I was sitting down the other day with a developer and he said to me, "James, DynamoDB is rubbish. It's really slow. I don't understand why you're suggesting we use it." And I said to him, "What are you trying to do with it? Let's have a look at the table you've created." And he created a table, a list of users in it, very similar to our use case. He'd keyed the user table on email address, just like we have. But what he was trying to do was find out a list of all the users in a particular department. And department was one of the attributes in his table, but it wasn't his partition key and it wasn't his sort key. So he was in the console and he was scanning the DynamoDB table for all the users in a given department. And it was taking ages to run. and his table was getting throttled and he was running out of read units, and he was saying, "James, this is rubbish. Why are we using this?" And I said to him, "You're using it in the wrong way." So let's look at the DynamoDB data model once again, because this is really, really important. We have tables. Tables are collections of data. Inside tables, we have individual entries. These are like rows. And inside items, we have attributes, and these are the properties associated with the entries. And storing data is just like JSON, so just like what we've been seeing in the previous video. If we had a movie table, we can have two JSON documents. They can be a completely different shape, have completely different attributes. All that matters that's consistent is whatever our primary key is. That could be title, it could be movie ID, it could be anything, but that's the only field that has to be there. So I want you to think about DynamoDB as a persistent map. When you're programming things for DynamoDB, when you're designing use cases for DynamoDB, imagine that it's a map or a dictionary, and the only thing it's doing for you is storing it persistently. So while a map or a dictionary is held in memory, this is obviously stored persistently and durably across 3 availability zones, 6 copies, blah, 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 but it's a map. Please think about it as a persistent map. Now, as we know, maps are just key value stores. That is a data structure where each element contains a unique key coupled with an object, the value. And they're designed to offer consistent or order 1 performance when retrieving data based on the key, because the key is usually hashed or indexed, and this is exactly what DynamoDB does. If you want to retrieve data based on something in the value part of a map, you need to iterate through all the possible keys and values until you find what you're looking for. So that means query time grows with the number of objects in the map, exactly like the developer I was talking about. This was the issue he had. As his table grew, his scan query was taking longer and longer, and he thought DynamoDB was rubbish. And DynamoDB works in this way because that's what it's designed to do. It's designed so you do a lookup on the key, not a scan for the value. That scan feature is really just there for debugging and for very infrequent operations. So in our user table data model, we've got 2 keys. We've got a partition key and we've got a sort key. So that means we can have multiple entries for Joe Bloggs 1234 for each of his logins if we wanted to. So we can retrieve all entries for Joe Bloggs sorted by login time, for example. The course info data model, however, only has 1 key, just the partition key, and that's the course ID. So we're only ever going to look up on this course ID. Now, so far, we've only accessed data based on partition key. And like I said, this is just like reading data based on a key in a map. DynamoDB refers to this operation as a query, which is a little bit cheeky because really it's just a get by key operation. DynamoDB also gives you the option to create tables with composite keys, and we've done that as well with a partition key and a sort key. And in our data model, this would allow for multiple entries for a single user ID. So as long as each user ID has a different last login time, we can have multiple entries in the user table. So if we want to take this further, this means our query operation can return multiple results. So we can also supply a filter expression along with our query. So this gets executed after a query has run, but before the results are returned. Another option is to use a range expression, which can be applied to a table's sort key. So we can say, get me all user logins between this time and this time. If you only use queries in your application, you can expect average response time in the region of 10 milliseconds up to 20 million requests per second. So think about that for a moment. You can run 20 million queries per second and all of them will come back in under 10 milliseconds. That is quite an engineering achievement. So that's everything I wanted to talk to you about in this video. Please feel free to move on to the next video where we're going to look at how we can run a scan operation for a data outside of the primary key. Welcome back and welcome to video 2, scanning for data outside of the primary key. So just like with a map, sometimes we need to access data when we don't know the key. With a map, we'd have to iterate over all the keys and check the value associated with each key until we find the data item we're interested in. Unfortunately with DynamoDB we have to do the same thing, and it's called a scan, and it's basically a for loop. So remember that scan will loop through every single element in your table and return values that match your filter expression. So this means, as I keep mentioning, as the table grows it will get slower and slower and consume more and more read capacity. So let's take a look at a few examples. So we can do this from the AWS console, or we can do this from the AWS CLI. So let's take a look at how we do it from the console first. So if we go over to our users table, for example, we can click on scan, and if we click start search, it's just going to return everything. Now what we can also do is start to filter based on attributes. So let's say we want to filter on first name. We do first name string equals James. If we click search, it's going to return the same thing. If we make this James 1, it doesn't return anything at all. Now this might look obvious and simple, but what you need to remember is this is actually iterating over all of our items in the background and searching for them and applying the filter to each. Now, of course, we've only got one element in the table, so it looks like it's happening very quickly. And this is exactly what happened with the developer that I spoke to just a few short weeks ago, because he said, oh, it worked really, really well when I only had a few items in the table. And I tested it, and I was like, well, it would. And then we loaded all of our production data into his table, and then his scan was taking forever. Now, of course, we can also do this from the command line. We use the AWS DynamoDB scan operation. So if we want to scan the whole table with no filter expression, it's going to return all of our objects. Well, we've only got one, but that's all of our objects. If we want to run a filter expression, we do the same thing. Specify the table name, specify the filter expression. So we specify the variables for our filter expression. One is first name, and the field is first name. And the expression attribute values, we say that the first name is a string, and we're looking for a value of James. So in our filter expression, attribute first name should be the same as the attribute value we passed in, which is James. So if we run that operation, it's going to return the James cross object. If we were to change this to Dave, obviously we would expect it not to return anything at all. So that's everything I wanted to show you in this video. Please feel free to move on to the next video, and we're going to do a performance analysis of queries against scans. Welcome back, and welcome to video 3, performance analysis, queries versus scans. So remember, a query is a lookup against an index. So fundamentally, the performance of a query against a single item is O1. That means that the time the query takes to return is unrelated to the number of elements in the table. So even if you've got 10 billion elements in the table, the query will still come back in O1 time. So that is less than 10 milliseconds. Of course, adding range expressions against sort keys and filter expressions against result sets adds to the execution time required by the database, because this gets executed server-side. DynamoDB guarantees average response times of around 10 milliseconds for query expressions. Scans are a different story altogether, and I keep banging on about this because it's absolutely essential that it's well understood. The performance of a scan is ON. That means the time the operation takes is directly proportional to the number of elements in the table. A DynamoDB scan operation can actually read every single element in the table, although you have the ability to limit the number of objects that will be returned. So you might think if you put a really restrictive filter expression on your scan operation, it's only going to scan a small number of items in the table. That's wrong. Filter expressions get executed after the scan has taken place. So there's nothing you can do to improve performance. Absolutely nothing. And this is a really, really fundamental important point to the use of DynamoDB. Scans touch every element in the table. Doesn't matter what filter expression you apply to it, the filter gets applied after the scan result. So the scan will iterate over every single element in the table. It won't stop if it reaches filter expressions or satisfies any expression that you've provided, because it will return every element initially and apply the filter after the scan has taken place. Remember that DynamoDB capacity is provisioned in terms of read and write capacity units. So a scan operation can consume all of the provision read for a large table in a single operation, meaning other parts of the application will be unable to utilize the table. And in general, using a scan is basically a completely unacceptable compromise and should really only be used in edge cases where you need to search for specific values on an ad hoc basis. So one last time, queries are good, scans are bad. Queries will come back in under 10 milliseconds regardless of the size of your table. Scan performance will grow as your table grows. If you need to use a scan regularly in your application, you've done something wrong. but there is a solution. And we're going to find out how to do it in the next video, where we're going to look at how we can access data outside of the primary key using a better method, something called a secondary index. Welcome back and welcome to video 4, accessing data outside of the primary key using secondary indexes. So we've talked a lot about why we shouldn't use scans, but we haven't really talked about what we should do if we need to use a scan. Well, there are alternatives, and there are quite often use cases where querying on the key alone isn't enough. And we've established that scanning a table is really only appropriate under ad hoc edge cases, and it's not something that should be baked into the application because it's bad. So how do we solve for use cases where we regularly need to query on other attributes in our table? Well, the solution is to create something called a secondary index. A secondary index is a synchronized data structure along with an alternative key. And there are two types of secondary index. A global secondary index, that's an index where the partition key and sort key are different from those on the base table. With a global secondary index, or GSI, queries can span all data across all partitions in the base table. The alternative is called a local secondary index, or LSI. An LSI is an index that has the same partition key but a different sort key. The LSI is considered local because every partition of an LSI is scoped to a base table partition that has the same partition key and value. And Amazon recently changed the limits on this, so you can now have up to 5 LSIs, but up to 20 GSIs per table. In terms of a bit more detail, a secondary index can be thought of like a second table that's synchronized with your base table. So basically what you get is a synchronized view of your base table with a different set of keys that you can query. You must specify and are charged additional read-write capacity units for the index, just like another table. Of course, it's eventually consistent. And the reason that it's eventually consistent is because under the hood, Amazon replicates the transaction logs from your base table and then applies them in real time to a second DynamoDB table. So let's take a look at what this means for us in practice. And I've created a simple example. So if you open part 4 under section 3, which is the video that we're on now, you can see I've made some changes to the SAM template. And the first thing that I've done is specified a global secondary index on our users table. So let's imagine we want to be able to look up users by email address. So what I've done is said, let's create an email index. The key schema this time, the hash key is email address instead of user ID. And we want to project all attributes, that is all values, from our base table into our secondary index. So what this means is if we want to look up a user by email address, we no longer need to scan for them, but we can query for them instead, which means we get the same order one query benefit that we were getting when we did a query on our base table. What I've also done is created a new Lambda function, get user by email. If I can find it, get user by email, here we go. So this is just another Lambda function. The path is going to be this time /users/email and then an email address in the path field. And if we go and look at the code for this, what we have to do is actually specify the name of the secondary index in the query. So all of this body here is exactly the same as the getUser function, but what I've done is I've specified an index name in the query method. So if we look at getUser for comparison, with getUser we just say table.query, here's the key condition expression. With getUser by email, we still do the key condition expression because we're doing a query, remember? But we specify an index in the index name. So let's have a go at deploying this. We can go back to our README. We're going to run a package command. Just make sure you're in the correct directory. So you should be in part 4 of section 3. So section 3, SAM package, uploads our changes to S3. And then we're going to run a deploy. Now, depending on the state of your existing table, this may fail. If it does fail, what you'll need to do is delete your CloudFormation stack and recreate it again. So I'm just going to run that. Let's see what happens. If it fails, I'll walk you through the deletion process. So that change has been successfully applied. So let's go and have a look at the AWS console first of all. If we just do a little refresh and click on indexes, we can see that our GSI is being created. Email index is being created with a partition key of email address now. We didn't have that before, so I'm just going to pause the video again while that creation process runs. Probably take a couple of moments. Okay, so that's now completed. I can see the email index is active. So what we want to do now is test that out. Let's call our API. So first of all, we know that we can do a get user based on a user ID. If we click send on that, that's going to load our user object. The email address is mail@jamescross.io. Now, let's say we want to get the user based on their email address instead of their user ID. We're going to call that new endpoint. So we're going to call slash email and then slash the email address, which was mail@jamescross.io. Let's just save that and let's give this a go. So there we can see the object comes back just as we expect. So this time it's slash users slash email and then the email address we're querying for. Obviously if we put something else in that field, it's going to come back with an error because the user doesn't exist. But we can see that we've now successfully queried our secondary index and we've been able to get some data back from our DynamoDB table that's not our primary key or our composite key, but without doing a scan. So this really, if you need to query an attribute that's not your primary key, this is the way to do it. So that's everything I wanted to show you in this video, and in fact everything I wanted to show you in this section. Please feel free to move on to the next section where we're going to be looking at some more advanced features like scaling your DynamoDB application, auto-scaling, global tables, and DAX. Welcome back and welcome to section 4, scaling your DynamoDB application, auto-scaling, global tables, and DAX. Welcome to video 1, the unit of performance in DynamoDB, provisioned capacity units. Let's briefly revisit what DynamoDB is, and this is important to get the context for the rest of this video. DynamoDB is a fully managed NoSQL database. So what that means is we don't have to worry about infrastructure, networking, servers, even virtual machines. It's not something we run on Amazon EC2. It's not something we have to host ourselves. It's not something we have to patch or upgrade or roll new releases to or anything like that. It's the closest thing that we can get to database as a service. So as we've seen with DynamoDB, the only interaction that we ever have with it is via an API. We never stand up infrastructure, we just call an API to send our data and to get our data back again. We never have to think about servers, we never thought about operating systems, we've never said we're going to run this on Ubuntu or Red Hat or anything like that. We've never made any consideration of networking, it's just something that we call over the internet. All we've done is configured the service and then consumed it directly via an API. Now under the hood, Amazon obviously needs to be able to manage capacity for each user's table, and then of course we have to pay for that, so they need to be able to bill for usage of that table and figure out how much DynamoDB we've consumed. So there are a few fundamentals around scaling that you should know about. And the way DynamoDB is provisioned is through capacity units, and there are two types of capacity unit. There's the read capacity unit and there's the write capacity unit. A read capacity unit is obviously the amount of read capacity you provision against your table. And this also applies to indexes. So remember we talked in the previous video about global and local secondary indexes. You need to apply read and write capacity to each of those indexes. And write capacity units, just like read capacity units, reference the amount of write capacity you provision against your table. And these also apply to indexes. And the last consideration is storage. Now this is not something that you have to configure in DynamoDB because Amazon manage it and scale it for you transparently. But the maximum amount of storage you can have for a single partition is 10 gigabytes. And this actually leads us to have an understanding of how Amazon build DynamoDB and how they provision it. So each partition is actually a node in the database cluster, and each of those nodes has 10 gig of high performance SSD storage. So firstly, a little more about read capacity units. If you decide to provision capacity yourself, you must choose how many units you want to allocate to a table. One read capacity unit represents one strongly consistent read or two eventually consistent reads for an item of up to 4 kilobytes in size. If the item is larger than 4 kilobytes, additional capacity units are consumed. Transactional reads consume 2 read capacity units for items up to 4 kilobytes. So you're charged a penalty of double if you decide to use a transactional read or a strongly consistent read. Read capacity units refill every second. So one read capacity unit gives you one strongly consistent read of a 4 kilobyte item per second. Now write capacity units work in a very similar way. One write capacity unit, or WCU, represents one write for an item up to 1 kilobyte in size. If the item is larger than 1 kilobyte, as with RCUs, additional WCUs units are consumed. Now transactional writes consume 2 write capacity units for items of up to 1 kilobyte, and again WCUs, as with RCUs, refill every second. So one WCU gives you one strongly consistent read per second. Now a key thing to note is the maximum allowable item size is 400 kilobytes. Writing one item of this size per second would require 400 WCUs. So do keep that in mind when you're writing to your DynamoDB table. Now our load on database tables is not always linear or predictable. So DynamoDB allows you to temporarily burst beyond your provision capacity. DynamoDB works by retaining up to 5 minutes of unused capacity units for you to use. And you can think about this like a bucket that refills but can only hold 5 minutes worth of capacity units. So for example, if you have a table configured with one RCU and the table remains idle for a 5-minute period, at the end of this period you will have accumulated 300 RCUs which are available in a rolling window for burst capacity. Remember now that DynamoDB is a distributed system and your provision capacity is distributed across all partitions in a given table. So let's say you've provisioned a table with 400 read capacity units and 400 write capacity units, and that table has 4 partitions. Each partition will be allocated 100 RCUs and 100 WCUs. If more than 100 RCUs or 100 WCUs are consumed on a given partition, it's going to start to get throttled. Now this is called a hot partition scenario, where read and write load is unevenly distributed. So Amazon have recently introduced a feature called DynamoDB Adaptive Capacity. And with adaptive capacity, Dynamo attempts to alleviate this issue by dynamically reallocating provision capacity to hot partitions. So we can see in this diagram, we've got 4 partitions. We've got a total provision capacity of 400 write capacity units, a total consumed capacity of 300 write capacity units. Now, on the first 3 partitions, we're only consuming 50 write capacity units. But on the 4th partition, we're consuming 150 write capacity units. So we're writing in an uneven partition pattern. So partition 4 is getting hot. So what DynamoDB will do within burstable constraints is it will provide additional capacity on those hot partitions to alleviate constraints. The last piece of the puzzle, of course, is the pricing model. So you pay for provision RCUs and WCUs as well as consume storage. And these are the prices for EU West 1, which is Ireland. So you pay $0.000147 per RCU per hour, which is about 10 cents a month, or about 53 cents per month per write capacity unit. On top of that, you pay just almost 30 cents, so 28 cents per gigabyte per month of storage, and the first 25 gig is free. So that's everything I want to talk about in this video. Please feel free to move on to the next video where we're going to talk about automatically responding to demand with auto-scaling and on-demand capacity. Welcome back and welcome to video 2. Automatically responding to demand, auto-scaling and on-demand capacity. So what happens when our consumption grows rapidly? And this is a common concern, particularly for technology startups who are worried about how they respond to scaling demand in their application. Eventually, insufficient provisioning will lead to failure. If you don't pre-provision sufficient capacity, either read capacity units or write capacity units, you're going to end up with a failure. The DynamoDB service, after you've consumed all of your burst capacity, will start to throttle your API calls. You're going to get exceptions in your application. If you're using one of the Amazon SDKs, you'll notice a throughput exceeded exception. The read or write operation will fail and your application is going to need to retry. And if you're consistently receiving these exceptions, you need to consider adjusting your provision capacity. Now, of course, we could do this manually, but this is cloud computing. Manually adjusting capacity and manually scaling isn't in the spirit of cloud computing, so that's not really something that we want to do. Now, fortunately, Amazon have thought about this for us, and Amazon offers us a choice of two solutions for this. One is called auto-scaling, and another is called on-demand consumption. So auto-scaling works a lot like auto-scaling virtual machines. You specify a baseline capacity and a target utilization. Amazon will try to adapt your provision throughput, both read and write capacity, over time to keep within these boundaries. So what that means is, essentially under the hood, Amazon's going to specify CloudWatch alarms on your read and write capacity. So if your consumption of either of those read or write units exceeds a certain metric that you've specified over a given period of time, Amazon's going to start to add more capacity to your table. The second option is called on-demand consumption, and this is really the closest thing you can get to database as a service. Serverless. It's like two levels of abstraction. You don't even have to think about read and write capacity units. So on-demand works a lot like auto-scaling, but it leverages a shared pre-provisioned fleet of resources to scale up much faster than auto-scaling does. So that means you don't have to wait for auto-scaling to react. And in my experience, auto-scaling can take 5, sometimes even 10 minutes to respond. And during that time, if you've got a really spiky workload, you could start to see exceptions in your application. On-demand consumption doesn't have that issue. So up to a limit, and it's a fairly high limit. I've seen 10, 20, 30,000 reads per second on a DynamoDB table. With on-demand consumption, Amazon is able to scale their back-end resources for you. So a little bit more first about auto-scaling. So just like scaling a fleet of virtual machines, DynamoDB auto-scaling allows you to create an Amazon auto-scaling policy for either or both of your RCU and WCU configurations. You specify minimum and maximum capacities, along with target utilization, and Amazon adapts capacity to try and match this profile. So we can see in this example at the bottom, you specify a target utilization as a percentage, a minimum provision capacity, and a maximum provision capacity, and you have the option to apply the same settings to global secondary indexes as well. Now, of course, that target utilization can be as wasteful or as tight to 100% as you like. So if you set it to 50%, that means that on average 50% of your utilization is not going to be used. So that means 50% of your capacity units will sit there idle. Now, if you move that closer to 100%, you're going to be more efficient with your utilization, but of course spikes in demand are likely to result in retries or errors in your application. So auto-scaling DynamoDB tables works just the same as auto-scaling virtual machines. So you create your DynamoDB table and you create an auto-scaling policy. DynamoDB will create a CloudWatch alarm that will monitor the DynamoDB capacity unit consumption versus provision throughput. Once it reaches the threshold that you've specified, Amazon will notify you that an auto-scaling action is about to occur. That auto-scaling action will then be triggered by CloudWatch, and that auto-scaling action will update the number of provision capacity units on your table. But of course, auto-scaling results in unutilized capacity, which you still have to pay for. And scaling can be slow. I've said seconds to minutes, but in my experience, it's usually minutes, sometimes 5, sometimes more minutes. And that means if your application utilization is really, really spiky, you could still end up with timeouts. This means you probably don't want to set your target utilization above 70% to allow for bursting and growth. But that means on average, you're paying for 30% unutilized capacity. And again, this is not really cloud. You're essentially still forward deploying capacity for peaks you don't know will happen. And the promise was when we went to the cloud, we wouldn't have to do that. We'd only pay for what we use, and we're still paying for something that we're not using. And this is where on-demand consumption comes into play. It's proper pay for what you use. Amazon manages the scalability of the back-end resources for us. They manage pre-deploying fleets of VMs or whatever they have to do. We don't have to worry about it. Pricing is based instead of on request units, is based on the number of requests you make, regardless of the number of requests per second. So you pay per request to the database rather than paying for provision capacity. And DynamoDB handles any required scaling as part of the service, making use of a large pre-provisioned database fleet. And you can consume up to 40,000 RCUs and up to 40,000 WCUs by default, but this can also be raised by contacting AWS support. So that's everything I wanted to talk about in this video. In the next video, we're going to talk about how to make an application even lower latency by employing in-memory caching with DAX. Welcome back and welcome to video 3. Make the user application low latency by employing in-memory caching with DAX. So what's the use case for caching? If your application consistently queries the same elements over and over and over again, it doesn't make sense to have them keep hitting DynamoDB every time. Perhaps you have an application use case where your read request rate needs to scale out to hundreds of thousands of requests per second, or even higher. Perhaps you want to just reduce the cost of your DynamoDB read capacity units. Or maybe your application is very sensitive to database read latency. Well, again, Amazon have a solution for us, and it's called the DynamoDB Accelerator, or DAX for short. DAX is a fully managed, highly available in-memory cache for DynamoDB that delivers up to 10 times performance improvement, from milliseconds to microseconds, even at millions of requests per second. And yes, I said that correctly, millions of requests per second. So DAX promises microsecond response time, even at extremely high request rates. So it's essentially a Redis cluster cache sitting in front of DynamoDB. It can scale out to millions of requests per second and beyond if needed. It's a fully managed service with a DynamoDB compatible API, and there's no need to modify your application code. You just put DAX in front of DynamoDB and everything will work. And DAX automatically manages tasks like cache invalidation, so developers don't have to worry about it. In terms of cache behavior, DAX is something called a write-through cache. So that means writes to DAX will update items in cache while persisting changes all the way through to the underlying DynamoDB table for resiliency. DAX requires you to specify a TTL for items, or time to live, and this is just the amount of time that they remain in cache before DAX will expire them and then make a request to the underlying table. Changes made to DynamoDB objects that are not written through DAX will not be reflected in cache until the object reaches its TTL or is expired in some other fashion, such as an LRU algorithm. So let's look at an example of a write-through behavior. So number 1, and we're looking at this diagram on the left-hand side here. Alice updates an item in the product catalog table. DAX forwards that request to DynamoDB and the update succeeds. DAX then writes the item to its own in-memory item cache and returns a successful response to Alice. From that point on, until the item is ultimately evicted from the cache, any user who reads the item from DAX will see the item with Alice's update. A short time later, Bob updates the same product catalog item that Alice wrote. However, Bob updates the item directly in DynamoDB. DAX does not automatically refresh its item cache in response to the updates via DynamoDB, and therefore DAX users do not see Bob's update. Alice reads the item from DAX again. The item is in the item cache, so DAX returns it to Alice without accessing the DynamoDB table. So what Alice will see is her update to product catalog. She won't see Bob's update because Bob has updated DynamoDB directly. So that's everything I wanted to talk about in this video. In the next video, we're going to talk about deploying our application around the world with Lambda and global tables. Welcome back and welcome to video 4, Going Global, deploying our application around the world with Lambda and global tables. A DynamoDB table lives in one region. What if our application is global? And there are lots of use cases for this. Loads of applications are global. Having your application make cross-region calls to a centralized DynamoDB database adds a ton of latency. And this results in slower responses and a worse user experience. And to be honest, most websites and applications these days are accessed all around the world. Global Tables aims to solve this problem by providing a local replica of your data. So DynamoDB Global Tables is multi-region, multi-master, and it offers fast local performance for distributed applications. So Global Tables enables you to automatically replicate your data across your choice of AWS regions, giving you a local table in region for your application to connect to. And it leverages DynamoDB streams for synchronizing changes between those tables. Global Tables is also a master-master model, which means you can write to or read from any endpoint, and DynamoDB handles those change synchronizations under the hood in an eventually consistent fashion. With Global Tables, you're building something that's truly globally resilient, and Amazon claims this is the first fully managed multi-master, multi-region database. So if you've got globally dispersed users, they hit what looks like a single application endpoint. Now, under the hood, you've probably used something like DNS to route users to endpoints that are local to them for better performance. So let's say you've got a replica in North America, another in Europe, and another in Asia. DynamoDB Global Tables allows you to build high-performance, globally distributed applications. It offers low-latency region writes to locally available tables, and it's completely disaster-proof because you get this multi-region redundancy. And within each region, DynamoDB is also distributed across 3 different availability zones. That means 3 different data centers and 6 copies of your data in each region. And it's easy to set up as well. There's no application rewrites required. You just reconfigure DynamoDB either using your infrastructure as code solution or on the console. And of course, you can integrate with Lambda for a truly global DR solution. AWS Lambda already manages resiliency across all availability zones in a single region. If you perform a global deployment of Lambda, where Lambda is your application compute layer, along with DynamoDB Global Tables, you have a truly global, highly available solution. And of course, the failure of an availability zone or a data center now is irrelevant to you. You won't even notice it. Even the failure of a region or multiple regions won't result in any downtime. Another region simply picks up the load and scales out transparently as required. So what are the requirements for global tables? Well, your table must have the same partition key as all the other replicas. The table must have the same write capacity management settings specified. The table must have the same name as all the other replicas. And the table must have DynamoDB streams enabled, with a stream containing both the new and the old images of the item. None of the replica tables in the global table can contain any data. Now, one of the problems with global tables is capacity planning. It can be a little bit tricky. Remember, each table needs sufficient write capacity units to apply all writes from all regions combined. Remember, this is a global synchronization effort. So if you've got 3 tables, each of them needs to have sufficient write capacity units to apply all writes globally. So let's say you have a table in America, another in Europe, and another in Asia. You're consuming 400 write capacity units on each of them from user requests. You actually need to provision 1200 write capacity units on all 3 tables, because DynamoDB needs to be able to apply each of those 400 writes per second to all 3 tables simultaneously. So to be honest, instead of worrying about this, you're probably better off considering using either auto-scaling or the on-demand capacity model, which of course takes care of all of this for us. Both of these approaches allow your table to scale transparently and respond automatically to demand. So that's everything I wanted to talk to you about in this video, and in fact everything I wanted to talk to you about in this section. Hopefully it's been a good overview of how DynamoDB works under the hood, some of the more advanced features that DynamoDB offers, and how DynamoDB really has the features to allow you to build a truly scalable, truly global application. Welcome back and welcome to section 5, building a data cache with DynamoDB and TTL. Welcome to video 1, creating a simple user authentication service. So what do we want to build? Well, we want to build a really simple user authentication service that allows us to do a couple of things: create new users, retrieve existing users, and log in existing users. So we're going to store some user information, obviously. So we want to be able to store particularly a user ID and some form of password. So we're not going to use a cryptographically secure way to store that password, but we're not going to store that password in plain text either. And of course, the login API functionality needs to validate our user's password. And then later on, we're going to issue an authentication token for each user based on that password. And that's a really common pattern for web services and web APIs. You don't normally supply your password with each request. That would be bad. Normally what you do is you log in and you get an authentication token, and OAuth is the most common way of doing this. You'll get an OAuth authentication bearer token, which you will pass along with each request. And that bearer token will be a cryptographically secure, randomly generated token, which will normally have an expiry as well. And that's where TTL will come into play a little bit later. So we'll get cryptographically secure bearer token, although for us it's just going to be some randomly generated string. And at some point in the future that will need to be expired. So that's what we're going to use DynamoDB's TTL, or time to live feature, for, to give those authentication tokens a limited time validity. So we're going to need, to begin with, to set the groundwork for this, we're going to need 3 API endpoints. We're going to need a put endpoint for users, so this will allow us to create new users in the DynamoDB users table. We're going to need a get endpoint to return information about existing users from the DynamoDB users table. Now this is going to return a 404, obviously, if the user ID requested doesn't exist. And then lastly, we're going to have a login endpoint. So eventually this is going to be used to issue an auth token, and we're going to see how we can do that in a couple of videos' time. But for now, we're just going to validate the user's password. If an invalid password is supplied, a 403 unauthorized will be returned, and if the user ID doesn't exist, a 404 will be returned. And each endpoint will have its own Lambda function. So following the same theme that we've been following to date, we're going to have a create user function, a get user function, and a login user function, and they will map on exactly to these 3 API endpoints. And we're obviously going to have an AWS SAM template that defines and creates all of these functions along with the DynamoDB users table. So without further ado, let's jump right into the code. So you can see I've got the code open here in Visual Studio Code. What I want you to do, if you're going to be following along, in the Git repository, open section 5. Under section 5, you'll find a part 1 section. And then inside part 1, we've got template.yaml. And template.yaml again is obviously our SAM template, and that defines the environment that we're going to be working in. We've obviously looked at this plenty of times before, so I'm just going to whip through this particular template and show you what we've created. So obviously we've got our DynamoDB users table keyed on user ID and last login. We've assigned that 2 read and 2 write capacity units. We've got our create user function here, obviously it's Python 3 again. The handler is create user.lambda handler. We've given it CRUD permissions on the user table, and we're saying that we want it to be triggered by the put to the /users API. And we've got the get user function. Again, everything's the same, but the API that's going to trigger it is /users, and then the path parameter user ID. That's obviously a get. And then lastly, we've got a post for login. So we're going to post to /users user ID /login. Code is very similar to the previous examples. So the create user lambda handler, obviously we retrieve the request body from the HTTP body. We pull out email address, first name, last name, and password. And then this create user function here, we'll call the DynamoDB create user function. And we're generating the last login time as now. And then we create this user doc with the user ID, which is a randomly generated UUID hex. Obviously email address, first name, last name from the payload. We're calling this encrypt password function. This is a little bit interesting. So we're using a SHA-256 signature on the password. So that's going to run a SHA-256 one-way hash against the password. Semi-secure, you could say. SHA-256 is pretty secure, but if you really wanted to do this properly, you should be adding a random salt to your password. So we're going to put that in there, and then obviously the last login time as well. Just logging that out to the console. And then we're calling the put item DynamoDB API function, which we're all very familiar with now. Get user works in exactly the same way. We're just doing a query, obviously a query because we look up by key. So we're saying find the first entry for this user ID, or rather get all entries for this user ID, and we're just going to return the first one because there shouldn't be any examples where we've got the same user ID in there twice. And then the last one, login user, is a little bit interesting. So it's very similar to get user, obviously. So we're doing a user lookup based on user ID, but what we are doing is we're validating password. So the methodology for that is very simple. Obviously get user by ID, and we have the same encrypt password function here, but what we're going to do is we're going to pass the candidate password in. That's the password that gets passed to the API endpoint. Run the same encryption algorithm over it, the SHA-256 one-way hash, and then compare that result with what's been stored in the database. So what that's achieving is, because it's a SHA-256, it's a secure one-way hash, there's no way for us to decrypt the password in the database. All we can do is compare it against candidate password. So that's how we're achieving that. So as before, what you need to do to deploy this in the correct working directory, you're going to run the SAM package command. That uploads a SAM package file to S3, and then we just run this. So SAM deploy, reference the template file, stack name I've called TTL demo, and capabilities I am to give it permissions to run that. Just hit enter, and I will pause the video while that change set is executed. Okay, so that's all run successfully. We can see successfully created stack. Now if we flick over to the AWS console, we can go and take a look at what's been created. So if we click on Lambda, we should see we've got get user, login user, and create user function. If we click on DynamoDB and click on tables, we can see we've got our user table here. And of course, as we know, what we actually need to be looking at is API gateway. So we can get our API gateway invoke URL. So click on TTL demo, again click on stages, click on prod, and you're just going to copy this invoke URL here. Now, if I flick all the way over to Postman, just copy that, flick over to Postman, and here's something I created earlier. So a create user example, so stick your URL in here. This is what your body is going to look like. If you click send, you can see you've asked me to create a user with da-da-da-da-da. This is our encrypted password, and here's the user ID. So just copy that user ID. If we pop over to get user, you can stick your user ID in here. You can see I've been testing this earlier. Click send, make sure obviously your invoke URL is correct, and you can see this is the user body. Now if we want to log in, obviously we've got the /users /user ID /login path. That's a post. So put your user ID in here. Just going to copy the invoke URL from this example. And here's the body. So the password we supplied was 1234. That's what we set the user with. And we can see now that it returns the body payload for our user that we just created. Now with a bit of luck, if we change this to something else, we add another character to our password and click send, you can see here we get a 403 forbidden. So this is a standard unauthorized response. So that's everything I wanted to show you in this video. Please feel free to move on to the next video where we're going to look at how we can create and issue those temporary authentication tokens. Welcome back and welcome to video 2, issuing temporary authentication tokens to users. So what normally happens when a user's logged in? Well, usually a system will grant users an authentication token once they've logged in, which they then pass with each request to the system or to the API. And this authentication token essentially acts as a surrogate to their password. And the reason for that is obviously the password is the master authentication token, as you like, and you really don't want to be passing that around with each request. So there's a couple of benefits to this. Obviously, one is that it's a surrogate to the password, and two is that we can expire authentication tokens, whereas you can't really expire a user's password every hour. So what that means is when a request is received, the system will need to validate that the supplied authentication token matches what was stored in the database. So what changes are we going to make? Well, we're going to make or add two new endpoints, one which generates an authentication and stores it in DynamoDB, and a second which validates an authentication token that's passed in a HTTP header against the token that's already stored in DynamoDB. So to do this, we're going to use an update expression to add a new auth token to a user profile, storing only one token per user. If the user logs in again, the previous token is going to be overwritten, and DynamoDB has a nice DSL for describing this behavior based on the update item operation. So we provide the key of the item we want to update, along with an expression indicating the attributes we're going to modify and the value that we will assign. So we want to set or overwrite a single attribute, which is auth token, and the expression to do this is set auth token equals token. And you'll notice that the update expression DSL is pretty similar to SQL, so it makes it very easy for us as developers to read and to use. So the update item API also needs the key for the item that's being updated, which obviously in this case is the user ID, which we'll pass along with the authentication token in the HTTP header. So let's go and take a look. So this time I want you to open part 2, and let's start with the template. So if we have a quick look through the template, we can see that it is, oops, that's part 3, getting ahead of myself. If you have a look at the template, you can see that it's basically the same as what we used before. The main difference is that we now have a validate auth function. So this function would ultimately be applied to every single API endpoint that you write. We haven't got a business logic API endpoint, as it were, so we've just called that some action, and what we're going to do is expect that the authentication token exists in the header. So in terms of changes to the code, well, first of all, the login function now needs to generate a token. So what I do, this is extremely insecure, so don't actually do it this way. I just create a random string of length 30 and obviously store that against the user object and then return it to the user. So this is where the update expression comes in. So if we just go right up to the top, what we're going to do is obviously validate the password. If it's invalid, we return a 403. If it's valid, we're going to create a new auth token. That's where this set auth token piece comes in. So set auth token obviously calls the token generator function, and then we run a DynamoDB update expression, and this is what it looks like. So first of all, we say set the key for the object that we're updating, which is user ID. We run an update expression on that, which is, as we discussed just a moment ago, set auth token equals token, and then we set the value of that token to be the token that was generated by the token generator function. And that's really all there is to it. And of course, we're then going to return that token to the user, and that's what this return values equals updated new thing does. If I was to put a response here, that response is going to contain the auth token. Obviously we know what the token is because we just created it, but it's a nice little additional feature to the API. So we will return that to the user. Of course, the second piece of new functionality is to validate that auth token. So we're expecting, let's say this is a business logic API, like get my favorite courses or something. User ID and auth token are going to be passed in the header. So we're going to extract those from the header. We're going to check that the auth token exists. If it doesn't exist, or rather, sorry, we're going to load the data for that user. And we're going to extract the auth token for that user. If they don't match, we'll return a 403, not authorized. If they do match, then we return a 200 and say auth token is valid. You can continue. So let's update our stack. So we're going to run SAM package. Oops, I'm still in part 1. So if we go into part 2, we can run SAM package again. We can run our SAM deploy again, and I'll just pause the video while that runs. So that's now finished running. If we head over to the AWS console and go to Lambda again, hopefully we should see we have one new Lambda. And we don't actually, and this is an important thing I wanted to point out. So if you look at the message here, it says failed to create or update stack. And there's a very good reason for that, and that's because we've changed the type of DynamoDB table we've got. So the sharp-eyed ones amongst you will notice that we've removed last login from our user key, from our DynamoDB key definition. Now, CloudFormation can't update an in-place DynamoDB table if the key definition has changed. So if we go over to CloudFormation, we can actually see that error message here. CloudFormation cannot update a stack when a custom name resource requires replacing. So how do we fix that? Well, we have to actually delete the old stack and then create it again. So I'm just going to click delete stack from the CloudFormation console. I'll wait for that to run, and I'll pause the video while it does. Okay, so that's just finished running for me. It took maybe about a minute. And what we're going to do is we're just going to repackage a stack and run a deploy again, and I'll just pause the video while that runs because that will take a couple of minutes. So that's now finished. Now hopefully if we go back and refresh on the Lambda console, we now have 4 functions, and we do. Now important note, obviously the invoke URL will have changed. So just head over back to API Gateway, click on Stages, click on Prod, and copy that over. And if anything, this highlights the importance of DNS. So now if we go back to our Postman console, obviously we need to create a user again. Just update that invoke URL, click Send. That's going to create a new user ID for us. So if we go to get user, we can test that that works. Obviously, again, we have to update our invoke URL, and we also have to copy our user ID again. You can see that fortunately that worked. Now we can take all of that URL, take it over to the login endpoint and paste that in. Now this has an invalid password in it, so again we still get a 403. If we make that password good and click send, we get an auth token now. So this is new functionality for us. We've now got an auth token. So now if we go over to auth user, that's prod, that's some action, so we just remove this from here. And in the header here, I've got an old user ID and an old auth token. So if I click send on that, I get a error because I obviously don't have permissions to access that function. If we now put a valid user ID in there, we'll get a 403 because the auth token doesn't match. If we now put our valid auth token in there, auth token is valid. So there we go. We've created a very, very simple authentication service where we can log in a user, issue an authentication token, and validate that authentication token. So that's everything I wanted to show you in this video. Please feel free to move on to the next video, the last one in this section, where we're going to use DynamoTTL to expire our authentication tokens. Welcome back and welcome to video 3, expiring user authentication tokens with DynamoDB TTL. So now we're getting into the meat of this section. So what is TTL? Well, TTL, or time to live for DynamoDB, allows you to define when items in a table expire so that they can automatically be deleted from the database. TTL adds no additional cost to using DynamoDB and provides a way to reduce storage usage by obviously eliminating old unused data, as well as the cost of storing irrelevant data without using provisioned throughput to delete items. So TTL is useful if you continuously accumulate data. So let's say, for example, if we're storing all authentication tokens a user had ever created. So how does TTL work? Well, DynamoDB runs a background job to check the TTL attributes of items to see if they're expired. And TTL compares the current time in epoch time format to the time stored in the TTL attribute of an item. If the epoch time value stored in the attribute is less than the current time, the item is marked as expired and will subsequently be deleted. Now, this doesn't happen immediately. DynamoDB typically deletes expired items within 48 hours of expiration. So if your use case calls for those items to be deleted immediately, you'll probably have to implement your own solution for that. Now, a delete operation is reflected in both local and global secondary indexes. So how does this relate to our use case? Well, we have two possible use cases for this. We can enable a TTL attribute on our users table and remove users that haven't logged in after a certain amount of time. That's a good way to annoy your users. Or we could create a second table containing auth information, mapping a user to a list of auth tokens in an auth table, each with their own TTL, and we expire auth tokens after a certain period of time. Now, the second example really makes a lot more sense, so we're going to modify our example code to follow this second approach. So what changes do we need to make? Well, we need to create a second table. We're going to call it user auths, and it's going to be keyed on user ID and then sorted by auth key. We're going to modify our login function to create an entry in the user auths table for each valid login. And we'll modify our validate auths function to check all user auth entries for a valid authentication token. And lastly, we're going to enable a TTL of 48 hours on the user auths table. So let's go and take a look at the code. Now, again, if we're modifying DynamoDB tables, the easiest way to make sure that you don't have any problems is just to delete your existing CloudFormation stack. So I'm going to delete that stack and leave that to run while I head over and show you the code. So you can close part 2 for now and open up part 3. So let's start with the template. So you'll notice here we've created a new table, that's the auth table. And as discussed, it's keyed on user ID, sorted by auth token. And the key part here for this video is that we've added this additional functionality. So time to live a specification. And the way this works is we set an expiry time, or rather we tell DynamoDB which attribute we want to run TTL against. So we're saying we want to run that against expiry time. So we will set an expiry time on each object. And once the current time is greater than whatever value is in whatever field you specify here, DynamoDB will mark the object for deletion. Now everything else in this template is the same, except of course that we've given our login function permissions to read and write to the auth table, and we've done the same with our validate auth function. So if we start off by looking at login user, what we now do when we create an auth token is we just generate a new one each time rather than overwriting the old one. So if we scroll down to set auth token, first of all we set an expiry time on that auth token as now plus 48 hours, so that's datetime.now plus time delta hours equals 48. We create an authentication token document, which has obviously got user ID, auth token, and expiry time. And notice that this expiry time is the same field name that we specified in our SAM template here, auth table expiry time. And then we just insert that item into the auth table. So it's a put item operation. And remember, it's keyed on both user ID and auth token. So that means it's essentially an append operation. So we'll have many authentication tokens for each user ID. And then the last obvious change is the validate auth function. So what this is now going to do is get a list of all authentication tokens for a given user ID. So remember, that's still a query operation. It's a lookup on user ID. And we return all items that match that. And then in our validate authentication token code, obviously we have to iterate over those auth tokens and look for a match. So what we do here, if any auth token in authentication token list, return a 200 auth token is valid. Obviously, otherwise return a 403. So now we can see our CloudFormation stack has been deleted. Remember to change directory into part 3. And then we can just repackage our application and redeploy it. And as always, I'm just going to pause the video while that runs. Okay, so that's now finished. If we go back to the console, click on Lambda, obviously we should see the same functions that we had before. But perhaps I guess the interesting part is DynamoDB. So let's have a look at that. If we click on tables, we can now see we have this auth table. What we can do, if we click onto the auth table and just search for TTL, you can see here that the time to live attribute on this table is expiry time. Obviously we can disable that, we don't want to do so. If we click on items, we can see that it's keyed by user ID and by auth token. So what we want to do to test this out, obviously invoke URL will have changed again. This is why DNS is so important. So let's just copy that invoke URL and head over to Postman. So before I run any of these examples, I'm just going to update this invoke URL. Stop me having to jump around all over the place. Just update that for each of these. Okay, so that's done. Obviously we need to create our user again, so we can just run that. If we want to test that works, obviously we can run a get on the user. We can see that works. Now we're going to need our user ID. So let's go and try and log that user in. If we click login, we can see we've got an auth token. Now let's run login a few times and then go and have a look at DynamoDB. And now remember that we're not updating a single auth token anymore. We're actually appending it. So I've created probably 10 there. So now if we go to the DynamoDB console, click on tables, click on auth table, click on items. Now you can see for my user ID, I've got lots of auth tokens. and they've all got a different expiry time. And if you hover over that, it's the 18th of April right now, and you can see that helpfully DynamoDB is telling me that it's going to expire on the 20th of April at 6:09 p.m. and if you look at my little clock up here, you can see that it's currently 6:10 p.m. on the 18th of April. So we can see that our expiry time has worked as we expect. Now if we go and obviously try and auth that user with any of these authentication tokens, that should work for us. And we saw auth token is valid. Oops, didn't update my user ID. That would be why. There we go. Auth token is valid. Obviously, if I pass a bad auth token in, you get a 403 forbidden. So that's everything I wanted to show you in this video, and actually everything I wanted to show you in this section. Hopefully you now have a good understanding of DynamoDB TTL and how it can be really useful for helping you clear out old data from your table. Please feel free to move on to the next section where we're going to look at exporting data for later retrieval with streams. Welcome back and welcome to section 6, exporting data for later retrieval with streams. Welcome to video 1, understanding DynamoDB streams as a mechanism for changed data capture. So we already know DynamoDB is a really great place to store application data. It's cheap, it's fast, it's really easy to scale, almost infinite scale, while being extremely fast and pretty flexible as well in terms of query patterns. But what if we want to use DynamoDB as a data source? For example, to seed a data warehouse or a data lake. Now, it's pretty common in business intelligence type use cases to need to join data from multiple application databases in a centralized store, commonly known as a data warehouse. And this is used to drive business intelligence, advanced analytics, and all kinds of downstream use cases. Obviously, DynamoDB is not the right kind of database for that. It's not designed to do that. So we need a mechanism for getting data out of DynamoDB and into one of these other kind of data stores. This is where DynamoDB streams come in. So DynamoDB streams provides a time-ordered sequence of item-level changes in any given DynamoDB table. Changes are deduplicated and immediately available for downstream consumption. And other databases, Oracle, IBM, etc., refer to this functionality as change data capture or CDC, and it's basically a way of making your application database an event source. So some typical use cases for streams, we might want to replicate changes across different regions. Now, as we know, this feature is built into global tables, but global tables actually was built on top of DynamoDB streams. DynamoDB streams can be used, or rather downstream sources can be used for calculating metrics, performing aggregations on DynamoDB data, etc. Remember, of course, that DynamoDB can't aggregate data itself, so if you have a use case that requires this, and there are lots of use cases that would require this, you need to first load the data somewhere else. Perhaps you want to notify a downstream system asynchronously that an update has occurred to a particular record. For example, if a customer signs up to your system, you might want to asynchronously trigger a welcome email based on your DynamoDB source data. Now, one of the really big features of DynamoDB streams is that it can be used to trigger a Lambda function. And of course, if we can trigger a Lambda function, we can do pretty much anything that we can dream of. It really opens up a whole new range of use cases. So we can now write code that responds or runs in response to asynchronous changes to DynamoDB tables. And of course, being Lambda, all of the scalability concerns are managed by Amazon. Kind of functionally similar to running a database trigger, but the difference is a Lambda function runs asynchronously, so there's no performance impact on the database itself. And Lambda functions can literally do anything that you can write code for. Copying data to S3, sending an email, sending an SMS, or if you really want, turning on your lights at home. So simple example, let's say we wanted to send an email each time a new entry hits DynamoDB. And in this example, we're capturing doggy barks in a DynamoDB table. Bit of a fun example, and sending an email each time a new bark hits that table. So we have some process that writes items to the bark table, which is obviously a DynamoDB table. We create a DynamoDB stream for that table. We subscribe a Lambda function to that called the push new bark function, for example. That DynamoDB function gets invoked each time a new event hits that DynamoDB stream. And of course, a new event hits that DynamoDB stream each time a write operation occurs to that DynamoDB table. So that function gets invoked with a new bark. The Lambda function then publishes that bark to a woofer topic, for example, which could then send an email to say a new user has barked or whatever. So that's everything I wanted to send you in this video. Please feel free to move on to the next video where we're going to talk about how we can enable streams on the DynamoDB table and have a look at the output of that DynamoDB stream. Welcome back and welcome to video 2, enabling streams on the DynamoDB table and inspecting the output format. So what are we going to build? Well, we already have a users table from section 5 and we have Lambda functions for creating and deleting users in that table, but we want to create a stream that gets updated each time a new user is inserted into the table. So we're going to write a Lambda function and subscribe to that stream, and the Lambda function will be invoked each time there's new data on the stream, and we're going to configure it to print the contents of the record. So what changes are we going to make? Well, we need to add an entry to the SAM template to create a new DynamoDB stream, and we'll of course also need to create a Lambda function to subscribe to this stream and print out the records in this stream. Now a note or something of interest, there are 4 types of stream that you can have on a DynamoDB table. You can have a keys only stream that contains only the key attributes of the modified item. You can have something called a new image, which contains the entire item as it appears after it was modified. You can have something called an old image, which, as you would guess, contains the entire item as it appeared before it was modified. Or you can have new and old images, which contain both the new and old images of the item. Old image is really only pertinent if you've updated an item and you want to see what's changed. So for us, we're going to be essentially just doing an append only type operation. So we'll just use the new image stream type. So let's go and take a look at how this works. Now the first thing I'm going to do is just head over to my AWS environment, click on CloudFormation. I'm going to delete the old stack, the TTL demo here that I had from section 5. So if you had that there, do just delete it before we get started. Then of course go to section 6, open up part 2, and let's take a look at the template. So we've just got the one users table now. We've got rid of the auth table. And really the thing that's changed here is we've added a stream specification. The stream view is going to be of type new image, which is what we talked about on the previous slide. And we've also added this DynamoDB stream processor function. Just like every other Lambda function we've ever used, we've created a Python 3 function, which I'll show you in a moment. But the important part is the event type. So the event type is DynamoDB, and the properties are that we want to invoke this whenever a change is made to the users table stream. So that's what this means. This is getting the ARN, Amazon resource name, of the stream for the users table. Starting position trim horizon means start as early as possible. And we've got the batch size actually set to 100 here. I'm just going to reduce that batch size to 1. And then of course we've got our create users function here as well. Now if we go and take a look at the process stream function, it's really simple. All it's going to do is get invoked, obviously, for each event that hits the stream. And for each event that hits the stream, we're going to print out the event ID, the event name, and the contents of the DynamoDB record. So obviously, in order to see that output, we'll need to go and look at the logs. So let's build that. So we can copy this. We're going to run, obviously, the usual SAM package command. Uploads that package to S3. Then we're going to run a SAM deploy command. And as usual, I'll just pause the video while that runs. Okay, so that's finished running. Let's go and have a look at the console and see what we've got. So obviously CloudFormation, we can see that stream demo stack. If we go to Lambda, we can see that we've got our create user function. We've got the DynamoDB stream processor function. Now if you click on that, under configuration, you can see that it's subscribed to DynamoDB. And if we go to DynamoDB, we can see our tables, we can see our user table, and we can see that we have a stream enabled with new image. So what we want to do, obviously we want to put some data into that DynamoDB table. Click on API Gateway and stream demo, and we obviously need to get hold of our invoke URL once again. So just copy that, head over to Postman, and we can use our create user endpoint from before. Obviously just replace the invoke endpoint, click on send, We can see it's created a new user as we would expect. So what we're going to do, we're just going to click that a few times. We're going to create a bunch of new users in our DynamoDB table, maybe 10, 15 or so, something like that. API is fairly snappy to respond. Click, 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 click. So now if we go over to DynamoDB, so click on tables, click on user table, click on items, and we can see we've got 24 users in our user table. Now, with a bit of luck, if we open our Lambda in a new tab, click on DynamoDB stream processor function, click on monitoring. Remember, this is the function that's subscribed to our DynamoDB stream. Click on view logs in CloudWatch and click on the top entry and just change that to text. And we can see that our function is being invoked each time a new user is created, and this is what the payload looks like. So we can see it's of type new image, we get the password, email address, user ID, login, last name, first name, and basically everything that's in the item that we inserted. So that's, if we just go back to row again, so we can see that this here is one single invocation of a Lambda function, and then we start another one here, and we can see this is getting invoked each time we create a entry in DynamoDB. So that's everything that I wanted to show you in this video. Please feel free to move on to the next video where we're going to look at how we can capture that data, transform it and export it to S3. Welcome back and welcome to video 3, capturing the stream data, transforming it and exporting it to S3. So what next? We know we can now subscribe a Lambda function to a DynamoDB stream, and we know what that stream contains. And we know the limitations of DynamoDB, particularly with respect to its inability to run aggregate functions, so count, sum, min, max and average and those sorts of things. You know, what if we wanted to, for example, find out how many users we had in our system? Now DynamoDB can show you a count of records in the table, but it's approximate and updated relatively infrequently. More complicated, what if we wanted to know how many times a new user was created in a given day or hour? Well, all of these functions require a different data store because they all require aggregations. They all require counts and filters and that sort of thing. And this is exactly what DynamoDB streams are built for. So Amazon S3 is, as we know, the most flexible storage medium in the AWS cloud. It's ridiculously reliable, ridiculously cheap, and offers almost infinite scale. So while we decide how we want to process our data, now I know how we're going to do this, but let's just say while we think about how we're going to process our data, let's use DynamoDB streams to export data in our DynamoDB table to S3 each time a new record is inserted. So we already have a Lambda function that gets executed on each record update to DynamoDB. So now let's just modify it to write those records out to S3. So of course we're going to need to create an S3 bucket, and we're going to need to give our function appropriate permissions to write to it. So let's go and take a look at the code. So we can close part 2 now, and just make sure you change your working directory to part 3 if you're following along. And I'm just going to close this for now. So let's start with the template. So first thing to notice is we've got an S3 bucket here, Calibri user sync bucket, and the second thing to notice here is our stream processor function has a S3 CRUD policy allowing it to create entries in that S3 bucket. So that's really the only thing that's changed in the SAM template, but the process stream function has changed quite a little bit. So before we were just logging out the data that we were receiving when our function was invoked. Now what we're doing is we are taking that data, we're creating a CSV record, we're storing that CSV record in /temp in our Lambda handler function, and then we're writing that data out to Amazon S3. So you can see there's a fair amount of code in here. So I'm just going to walk you through what's happening. Now the first thing to note is that Lambdas can be invoked with batches of events, so that's why there's an outer for loop here. So for each record in records, do the following. So the first thing we're going to do is we're going to create a dictionary of the data in that record. So all that does, this get data function, so we pass it the DynamoDB record that we were invoked with, that the function was invoked with, and we extract all of the attributes that we're interested in. So the way DynamoDB structures that, you'll notice from the log, was a bit weird. So we get these data type parameters in here as well. We don't really care about, but we want to get the create time, user ID, email address, first name, and last login. And we're just going to stick that into a Python dictionary. So that's what we get back from this function. Now if we go to look at write CSV, scroll down a bit further, what we're going to do is we're going to create a CSV file. It's going to have the file name users and then current timestamp.csv. We're going to store that in the local Lambda functions temp folder directory, which is just /temp. You can see I've set right at the top here, /temp. So it's going to go in /temp /users_time.csv. And then we're just going to open a write file handler to that file path, use the dict writer, which is a built-in function to write a CSV, a dictionary to CSV. We're going to write the header, and then we're going to write the row. There's only going to be one row, and then we're just going to return the file name. So this function returns the temporary file name, and then the last piece is just to write that out to S3. So what we're going to do is we're going to pick that file up from our temporary directory, and then we're going to use the Boto3 client to upload that file to S3. Now, of course, as always, we need to repackage our stack because we've changed the code. We shouldn't need to delete anything this time because all we've done is updated the code. Run sound deploy, and I'm just going to pause the video while that executes. So that's finished executing. If we head over to the console and go to S3, we should see we've got a shiny new S3 bucket in there. Here we go, stream demo Calibri user sync bucket, and then a random string that Amazon have generated for us. So if we head over to Postman, this should just work. If we start creating users, so it's going to take a little bit longer to run our function because it's now doing a little bit more, but still coming back around 100 milliseconds. So I'm just going to run this a few more times. Now go to DynamoDB, tables, users. Last time we had about 24 items in there. Now we've got 40 items in there. So now if we just go back to S3, if everything's worked as we would hope, we should see some files in there. So there we go. We can see we've got CSV files for each of the new users that we've created. So let's just download one of these and take a look and see what it looks like. So I've downloaded that. I'm just going to open this with Excel. And there we go. We can see that our Excel CSV file contains all the data that we inserted into S3, and that's now stored in an S3 bucket. So that's everything I wanted to show you in this video. Please feel free to move on to the next video where we're going to use a new technology called Athena to query that data in S3, perform some of those aggregation functions that I was talking to you about. Welcome back and welcome to video 4, querying the DynamoDB stream data with Amazon Athena. So what is Athena? Well, Athena allows us to run SQL queries against data that's stored in S3. So we've now demonstrated how to stream data changes from DynamoDB to S3 in near real time, and we saw how quickly it got updated. Now if we combine that functionality with Athena, we essentially have the ability to run SQL queries against DynamoDB data in an eventually consistent way. So you write data to DynamoDB, you want to run SQL queries on it. Well, DynamoDB doesn't offer that functionality, but we've shown how we can stream data from DynamoDB into S3, and with Athena we can then run that SQL query. So that means we get around some of the limitations of DynamoDB, not having the ability to run min, max, sum, count, average, etc. We just put the data somewhere else and then we have the power to do that. So how do we use Athena? Well, Athena works hand in hand with another Amazon service called Glue. So in order for Athena to be able to query our data, it first needs to understand what data is in S3, where the data is, and what format it's in. And that's where Glue comes in. So Glue offers a metadata service for Athena, and Athena can then be used to query the data just like you'd query data in any relational database. So let's go and take a look at how that would work. So let's head over to the AWS console, and what we're going to do is we're going to click on Services, and we're going to type Athena into the box here and click on Athena. So you get this nice little query page. And what it allows us to do is it allows us to write queries that run against S3 data. So the first thing we need to do is create a database. It's a virtual database. So we're going to say create database hands on Dynamo and run that. And you can see the database picker on the left hand side here updates. And now we want to create a new table. Now I've already written the query to do this, and I'm going to walk you through what each line means. So I just paste this in here. Helps if I get the first character. So create external table, so that's user table, and then this is the schema: create time, user ID, email address, first name, and last login. We're saying the row format is OpenCSV. Now we don't need to get into too much detail with this, but SERDI is basically a serializer deserializer engine for Athena. So what it's doing is basically telling Athena how to decode the data files. So Athena supports lots of different file formats: CSV, tab delimited, Parquet. We can use different kinds of compression. We can use Avro, various binary formats as well. What this Java class is doing is basically it's got a common interface and it understands how to decode that file. So with properties, we're saying the separated character is obviously a comma. Escape character we don't need to worry about. This is the location. So I'll just need to go back to S3 and copy the name of the bucket because it will have changed. So copy in whatever bucket name you get from here and just put that into this piece here. And then table properties, we're saying we want to skip the header line because every CSV file will have the header row. Obviously we don't want that to show in our result sets. So I'm just going to run that. That creates the table for us. So now if we do something like select star from user table, take a few seconds to run, and we can see here we have all of the data that we inserted. Now a couple of simple examples, of course. Say we wanted to count the number of records in that user table. We can run this simple count query here, get the max create time, average create time, etc. We can see we've got 16 users. This is the maximum create time. This is the average create time. So that's everything I wanted to show you in this video and everything I wanted to show you in this section. Please feel free to move on to the next section where we're going to look at how we can create transactions against DynamoDB tables. Welcome back and welcome to section 7, maintaining ACID compliance with DynamoDB transactions. Welcome to video 1. What is ACID and why is it difficult to achieve in a distributed system like Dynamo? Well, firstly, I guess we need to take a step back and understand what ACID is. So ACID is really all about ensuring the consistency of data. And it's something that you kind of take for granted because it comes pretty much for free in most traditional relational database models. But with distributed systems like DynamoDB, you don't really tend to find that they're ACID compliant. And most NoSQL databases are distributed and therefore don't tend to be ACID compliant. So what does ACID mean? Well, the A stands for atomicity. So that means transactions are either all or nothing. So you can never end up in a situation where part of your transaction succeeds. So if we think about like an airline booking system or a hotel booking system, for example, it's no good if the booking goes through, but they forget to take your payment data because that part of the transaction fails. Or if you're booking tickets for a concert, they might end up overselling their tickets because the part of the system that deducts tickets from the ticket availability table, a transaction there failed. Another part of the transaction succeeded and it told you that the booking had gone through, but actually it hadn't. So, that's what atomicity means. Consistency means only valid data is saved. So what that means is every time a transaction is acknowledged, it means as soon as another transaction comes along to read it, the response shows the whole result of that transaction and never a partial result of that transaction. And isolation kind of ties into that. So it means that no two transactions can interfere with each other. So you can't end up with a transaction updating another transaction's data while the first transaction is in flight. And the last thing is durability. So what that means is once a data is written, it will not be lost. So as soon as the database has acknowledged the right operation, it's safely stored and persistently stored. So with ACID, really everything revolves around transactions. So a transaction is a collection of read or write operations that succeed only if all other operations in the transaction succeed. And if any of those single operations fail, all preceding operations in the transaction will be rolled back. And we can see an example of that here in this diagram. So the first transaction, all of these three operations, 1 to n operations occur, they all succeed, and then there's a commit, and that makes those transaction operations available to other operations. Whereas on the one on the right, the second operation fails, so nothing gets committed. And that allows concurrent transactions to be isolated from one another. And if you combine all of these things together, it means a database is able to offer ACID guarantees. So how does this work? Well, when you start a transaction, the database engine will need to create locks on the records that you are about to modify in that transaction. And this is to ensure that other operations don't attempt to change them while your transaction is executing. The database will then attempt to apply each step of the transaction in a way that's only visible to you. And that's important because you don't want other transactions to see the effect of partially committed changes, because that would break the consistency rule from ACID. Now, if any of the steps in your transaction fails, all previous steps will be discarded or rolled back. And at the end of the transaction, there's a commit statement. At that point, all changes in your transaction are committed atomically. So that means they all go through at the same time. And everything in that transaction then immediately becomes available to other operations and other transactions. Now, all of this is usually possible because all data resides on a single server. But DynamoDB is distributed. Data doesn't reside on a single server. In fact, it resides on many, many servers. So that means we need a more complicated protocol for performing commits. So in a relational database, if we have multiple shards or multiple database engines, we perform what's called a three-phase commit. Now, Amazon haven't released how they've implemented transactions in DynamoDB, but it's very likely it follows something based on the 3PC protocol. So the way the three-phase commit works is that the database engine has to elect a coordinator node, and the coordinator node is responsible for making sure that the operation goes through successfully. So the first thing it will do is it will ask all participants if it can commit. So this is after the transaction steps have been applied. It'll ask them all if it can commit. If any of them don't respond, that's counted as a no. So a timeout causes the transaction to abort. The next thing it will do, the coordinator will send a commit authorized message. So there'll be a pre-commit message, and all participants will then have to respond to say yes, they're prepared to commit the change. And again, a timeout causes it to fail. And the last step is the coordinator will ask or will tell all nodes to actually go ahead and commit, and they should all respond to say that they have committed. So that's the three phase. You have the can commit, the pre-commit, and the do commit. Now, a couple of notes about transactions in DynamoDB. A transaction can contain up to 10 operations in any combination of get, put, update, delete, or condition check. If any object in a transaction is being modified while the transaction is in progress, the transaction will fail. And that's really, really key. So lots of relational database systems will lock items that are being modified in a transaction. So if anything else tries to modify them, they get queued up. But what happens here is DynamoDB doesn't lock the item, but it means that if somebody goes to update that item while the transaction is in progress, the transaction will fail. Now, you can target multiple items in multiple tables, which is a really, really cool feature, as long as they're in the same region and the same account. But no actions in a transaction can target the same item. So, for example, you can't condition check and update the same item. So that's everything for this video. Feel free to move on to the next video where we'll talk about how we can actually run a transactional read and a transactional write against DynamoDB. Welcome back and welcome to video 2, running transactional reads and writes against DynamoDB. So what are we going to build? Well, we're going to go back to our users and favorite courses example. So remember previously we used to create a course and then we had a second API call to add that course to a user's list of favorite courses. Well, we're going to modify our code to use the transaction write items API to perform both operations transactionally in a single call. We'll also modify our code to load users transactionally using the transact get items API. So let's go and take a look at the code. And now this is quite cool. So if you remember previously, if we wanted to add a user's favorite course, what we had to do is first call the create course API, which created an entry in the courses table. We then had to call the favorite course API, to add that course ID to the user table. Well, what we're doing here is we're using transactions to combine both of those events into a single API call. Now, unfortunately, DynamoDB haven't yet updated their table client to enable you to do transactions natively. So there are two ways of working with DynamoDB with Boto 3, which is the official DynamoDB SDK. One is that you can use the DynamoDB table client. So this is what we have here. So we do dynamodb.table, and then we can do usertable.query, usertable.put, and so on. It's a very nice, fluent API. And that's kind of a wrapper around the DynamoDB client. Now, unfortunately, this table API hasn't yet been updated to support transactions. And that's probably because, well, a transaction could quite often span multiple tables. So what that means is we have to use the Boto 3 client directly, and that's a little bit more complicated. So if we go down to this add course function, you can see here that we're now taking all the details we need for a course, and we're creating this course document. And you'll notice the syntax here is a little bit messy because DynamoDB expects you to tell it what data type you're passing in if you use the Boto 3 client. Now, the DynamoDB table API actually does this for you. It implies the data type, but whereas the client doesn't. So we have to tell it. So what this means is the course ID is of type string and the value is course ID, the title string, course ID, and so on. So the S means a string. You can also have number, you can have list, Boolean, date, and so on. And this is where it gets a little bit complicated. So what we're doing is we're saying client.transactWrite items, and we're saying these are the transaction items we want to occur atomically. This is what goes back to our ACID theory and our transaction theory. What we do in a transaction is we supply a list of steps that we want to apply, and we want those steps to all occur transactionally and in atomic fashion. So the steps that we need, obviously we need to do a put on the course table, and we need to do an update on the user table. So the put, so we're going to put this course document into the course table, and we're going to update our user ID in the users table, and we need to supply both the user ID and the last login. And then we run our update expression, which is to set a new element in the list, where the list is of favorite courses, and the value is course ID. And you can see the syntax here of this API is really not very developer friendly. We've got 1, 2, 3, 4, 5, 6, 7 indentations to get down to what we need to do. So hopefully Amazon are going to update the SDK to make something a little bit more user friendly, because for now we have to supply this great whacking JSON document to describe what we want to do. So it's not very fluent, it takes a little bit of messing around to get it right, but unfortunately that's just what we're working with. Particularly, you'll notice here we've used a data type L. That's because our favorite course list is actually an array. Now, get user transactionally is fortunately a much simpler operation, but with the same messy API. So we do client.transactGetItems. Now we're only getting a single item here, so it's not a particularly exciting example. Obviously we're getting our user by user ID by last login from the user table. So that's everything I wanted to show you in this video and everything I wanted to show you in this section. Hopefully you now have a good understanding of what ACID means, what transactions mean, the limitations and difficulty of running transactions on a distributed system, and how the DynamoDB API allows us to overcome that, as well as getting an appreciation for how that API is perhaps not the most developer friendly, at least compared to the DynamoDB table API.